Today, our keynote speaker is Professor Dr. K.M. Singh from IIT Roorkee. The topic of his plenary talk is finite volume-based heuristic approach for multiphysics optimization. Dr. K.M. Singh is a professor in the Department of Mechanical and Industrial Engineering at IIT Roorkee. He graduated from IIT BHU Varanasi and obtained MTech and PhD from IIT Kanpur. He has worked in academia and industry across the globe in countries like the United Kingdom, Japan, and of course India. He was a senior visiting researcher and HIVIPS fellow at Hitachi Research Group, Hitachi Limited, based in Japan. He is also an honorary visiting lecturer and postdoctoral research assistant at Queen Mary University of London, based in the UK. He is also a JSPS fellow and an assistant professor at Shinshu University, Nagano, Japan. His main interest areas are computational mechanics, fluid dynamics, renewable energy, sustainable development, and CAD thermofluid systems. He's a fellow of Institution of Engineers and a senior member of the AIAA. Now I'd like to invite Professor Dr. K.M. Singh to deliver his plenary talk. Please, sir, join us on stage.
Okay, thank you, Manu. Thanks for your kind introduction. Okay, so namaskar. So a very warm welcome to all of you in this morning session. And at the outset, I would like to express my sincere gratitude and thanks to the organizer, Professor Dr. Basant C. Karwar, who has, and his team of colleagues and volunteers who have organized this beautiful event. And it's been a pleasure to be associated with Basant. I have been associated with him since 2006 in various capacities as a teacher, mentor, and colleague. Without much further ado, I'll just start with today's presentation. It would be a fairly simple talk for the students. Mathematics I have kept to a very minimum, though now I realize that I did some I didn't do justice to the keywords which I put there, finite volume, because there's no slide which discusses in detail what the finite volume method is, thinking that most of the students they will know it. And multiphysics here is a very confusing term, but I have just for the sake of it, I've used this. We would be confining ourselves to this talk primarily to approach that's the heat produced by electrical effects. It was essentially an industrial research project sponsored by Hitachi India Limited for their partner company for a specific application being electric vehicles. So this is the back sort of outline of the talk. We will first have a brief look at what were the background and our objectives. And I will briefly enumerate what are different optimization techniques for topology optimization, a brief overview of governing equations which we have used in our multiphysics simulation, and then a brief outline of numerical methodology which we have used. And I would be presenting two optimization approaches in addition to the heuristic keyword which I have mentioned in the beginning, and then few examples of the simple optimization geometries, followed by concluding remarks. Now, background is very simple. This came from industry partner, and their critical concern is specifically with the so much of hoopla nowadays surrounding electric vehicles. Okay, so there's lots of issues related to thermal management. If you are aware, there are some electric vehicles which have got a range of more than 600 kilometers. And if that is the situation, for instance, Audi has got what it calls e-tron SUV. It's an SUV which is capable of cruising the speeds in excess of 200 kilometers per hour, entirely on batteries. So you can imagine the battery power, the amount of power which would be stored in the batteries. And similarly, the transmission currents which would be involved, like battery supplies DC current, and that DC current has to be converted by an inverter into AC current. And those AC currents are supplied to the motors which will drive the wheels of the electric car. DC currents would be typically in the order of hundreds of amperes. So they were even the simple connectors. Their design becomes very crucial because if they overheat, that will lead to lots of problems. If to avoid the overheating, if we use broader connectors, those would become fairly heavy. In the case of Audi, cost would not be that much of a factor. For other electric vehicles, as the cost would also be one of the concerns because those connectors would be of pure copper on DC side. On AC side, there will be laminates of copper. So copper is a fairly expensive material. It's also has got a weight. So now these are two perspectives in which, with which the industry partner approached us. That can we do something that we can reduce the material without compromising on the temperature aspect, that because temperatures have to be limited to a certain extent, and there are no forced cooling involved. So we'll have to just think about what happens in the natural cooling scenario and what could be the optimum geometries. So we first took up the DC part, and that's what I'm going to present today. And here we have to also be mindful of one fact that as temperature increases, for all, this is true for most of the conductors, the conductivity decreases because resistivity would increase, and then that would lead to higher heat. Okay. And sometimes we have also got adhesives bond these conducting plates to the integrated circuits or dielectric material. So if the temperatures reach a certain threshold value, that will damage the entire structure. So that's why it is very important that we maintain what we call the manufacturer's set temperature limits. Those must not be exceeded by our connectors. And this was the background or the focus of this research. And I just mentioned earlier that weight and cost, the C time thing, we would like to keep the weight to as low as possible in the case of electric vehicles. But once we've got this optimum conception or optimal conception with minimum material, that will serve both the jobs. It will reduce the weight. It will also reduce the cost significantly. But we have to ensure that the thermal management aspects are not compromised. That's a non-negotiable here. Okay. And it was in this context that we tried, we thought of using topology optimization. In fact, in the beginning, when we started our discussions, it was sort of developing a simple toolbox for the industrial designer. Okay, most of the connectors are what we call bus bars. Those would be planar copper elements. Okay. He said, can we try and think about reducing them bit by bit, and see where is the limit where our thermal management threshold would end. So that was the beginning of our heuristic thermal optimization of these electrical bus bars, that we would try to reduce those portions of the bus bar or connector where the current flow is not that high, the current densities are low. And that was the basis of our heuristic approach. We got significant weight reduction, we were not satisfied, then we also applied some formal topology optimization techniques in the next revision. So just a brief overview of what is topology optimization. So it's essentially a procedure to optimize the distribution of material to achieve the best result, satisfying the physical constants based on the physics of the problem. So this topology optimization is used in many engineering fields. The context would be different. For instance, the structural context, we would like to have a stiff and a strong element, a structural element. Okay. So there the physics would be our deformation. Similarly, in our context, it is thermoelectric effect. Similarly, if you've got a heat sink device, there it will be fluid flow and heat transfer. So that will be the physics involved, which will dictate our optimization process. So topology optimization, it originated in the beginning, long back. If you go to theoretical beginnings, it originated sometimes in beginning of 20th century. But the formal topology optimization processes, they have become popular only after the computer-aided design applications became dominant in 1980s. Okay, So, but now it has been extended to variety of applications, including structural, heat transfer, electromagnetics, and so on. And the research has been done with respect to different optimization approaches, and also what are different techniques which we can incorporate to improve the process. So I'll just give you a few outline, a few simple examples. Like this is a simple cantilever beam. So structural engineers, they will start from blank, and they would like to have an optimal distribution. So for instance, right inside, what you see, the white portions, they indicate there's no material there, and the black portion or the gray dark portion, that indicates the presence of material. And in this process, the beginning is just a simple blank, sort of a sheet we have taken, and from that sheet, this cantilever is carved out. Okay. A typical example of this you could also see nowadays in our car wheels. You will see a variety of shapes in our car wheels. They're very, very intricate shapes, sometimes very strange shapes. So from where those shapes come? Any problems? Okay. Similarly, let's a simple bell crank mechanism, and this example has been taken from ANSYS. ANSYS has incorporated topology optimization of structural as well as thermofluid elements. So they have got a separate module available. And COMSOL has got one which incorporates majority of multiphysics, including electromagnetic effects. So this is one example. We start with the leftmost figure. It has got plenty of material, reduce it further and further. And the rightmost one is the final design, which satisfies all the strength requirements and stiffness requirements of this joint. So in topology optimization, we are not compromising on the strength and stiffness aspect. We are just optimizing on the redistribution of material and reduction of the material and weight. Okay. And here we have in a structural application, normally we use the term compliance, that we minimize the compliance to obtain the optimal structure. And please remember, optimal solutions are not unique. In fact, most of the designs are, like, we can have a number of designs satisfying our requirements or our specifications. So similarly, it is not like a simple maxima minimum calculus that we have got for a given function. We've got a single maxima or single minima. We can have variety of designs which can satisfy, which can give us that same value of minimum compliance. So designs could vary. And that's why I told you earlier that you'll find nowadays the alloy wheels having very crazy designs. Okay? And they're all satisfy the strength requirements, and depending on the designer, depending on the car company, we've got different designs of the wheels. Similarly, this is one example taken from literature about the heat sink, and this was a numerical study, for instance here. So they took, this was the starting region, and for symmetry purposes, only the upper part was analyzed. The lower part was obtained by the mirror image. So here this slight reversal of the tradition the authors have used. They have used this dark portions, they represent no material, and white portions, they represent material of that heat sink. Okay, so here also you can see that nearly 50% material has been reduced from the required heat sink. Similarly, this one French group led by Pierre et al., they have also tried it in electromechanical or electrothermal applications. So this is an example for bus bar. They have considered a laminated bus bar, and the current densities were much lower than what we were planning to use. And here they have also used the darker portion represents no material, and the lighter gray portion that represents solid material or the material of the connector. And this white portions are where some other capacitors and other devices are connected. So starting the left part is the starting design. Can I use the pointer here? Yeah. So this was the starting problem domain, and then this was the final design. In most of the topology optimization approaches, we start with fixed solution domain. Okay. So solution domain is usually maybe a simple rectangle, and the shapes would be obtained as a part of the design process or optimization process. At most in the solid, we will have certain holes For instance, in this case, those would be the placement of different connectors, or in the case of wheel design or design of that bell crank device which you saw earlier, we would start with certain holes to begin with. And this is just a snapshot of few recent work what people have been trying to do. It started with structural design by Benso in 1988. And recently, people have been trying different methods, like for instance, level set methods to obtain the outline of our final structure. And some people have coupled level sets with what we call density-based approaches and so on. And applications, structures. Okay. Now you have got this is a fictitious interface energy-based application, thermal fluids. Then again, thermal fluid problems, applications. This is laminated bus bar for power converters, which is similar to our problem. Then this is one based on Lee derivative by Hussey et al. They have tried to optimize the design of our entire electromagnetic structure used in generators and motors. Okay. So they used a specific different approach, which they call Lee derivative, and based on that, they performed the optimization process. Other processes that people have suggested based on on-off method, and it's again based for synchronous AC motor. People have also tried it for design of magnetic cores for wireless power transfer devices, then weight formulation optimization, heat sink design of the rotor, how the permanent magnet in a rotor should be there. They have also applied it to the composite material, bionic applications. Okay. This last one is again a structural application, but based on slightly different. Okay. And still lots of work is going on. There are two such types of work which are research going on. One is application area, and the second one is improving the existing methods or devising new methods. So new methods are primarily based on the modifications of the initial methods suggested by Benso, that is a density-based approach, and based on other ones have been level set on a Minkert theorem, genetic algorithms, and so on. Now I'll come back to our objectives. Our objective was very simple. Develop a topology optimization framework for the optimal material distribution for DC bus bar. And the mandate which was given to us was that, look, it must not be based on a commercial software. So we have to develop all the required components ourselves, including the physics solver, the topology optimization solver module, and we also supplied them by a graphical user interface wherein the initial geometry modeling can be done, analysis results could be seen, and the final result could be visualized. And we were told that, look, your optimal configuration must ensure minimum amount of material. For instance, in our case, it will be copper. And this constraint must be satisfied. We were given certain maximum temperatures which shouldn't exceed in our design. So these were our objectives. With these objectives, we started our development. So we first, PhD students, we first developed a finite element solver. I developed a finite volume solver. And of course, we have now developed two different sets. One is based on finite volume approach, other based on the finite element approach. And we tried two different approaches. To start with, the first one, we put heuristic material minimization approach based on temperature distribution and based on the current density in the bus bar. And then later on, we incorporated formal topology optimization approach based on sensitivity analysis and method of moving acceptors. For physics simulation, we have developed two distinct components, two distinct modules, one based on finite volume method and other one based on finite element method. And today I'll be giving some results based on both of these. Our finite volume module was based on a domain decomposition approach, cell-centered finite volume methods. And the reason for this domain decomposition based design was that we thought we should also be able to parallelize it, because nowadays majority of our workstations, they have multi-core. Even simple laptop will have 6 to 8 cores. If you got a MacBook Air with M3 processor, it will typically have 12 cores. And your normal application, they would be running on only one core. Workstation would typically come with 24 or 32 cores. So our task would be that can we parallelize it so that we can utilize all the cores and the designer can get the result very quickly by using all the parallel cores. So keeping that in mind, we developed our finite volume solver, and similarly, the finite element solver is based on a similar approach. And there are certain things which we had to keep in mind while performing our experiments. That is to say, we were told that, look, please be careful, perform your simulations and give a design based on the maximum power, converter power possible, which will give us the best, what we call worst case scenario. And typical current densities which we will encounter would be in excess of 10 amperes per millimeter square. Remember when I gave the example of Audi, the typical currents on DC side are in hundreds of amperes. Okay. Around 1000 ampere. That was the worst case scenario for which experiments. And we also need to keep in mind that once we have done that so-called optimal design, we will again perform the physics analysis. And if we find the temperatures are too low, that means that we still not got an optimal design. We're still wasting lots of material because that will be an oversized system. It will be expensive as well as the weight would also be large. Okay, but however, we also need to worry about, again, this point was reinforced to us again and again that please be careful with the maximum limiting value. Now, just a brief overview of different optimization techniques. The most popular one is what we call density-based optimization. That here in what people simply do in density-based optimization is that entire domain, we will take a simple rectangular domain, and density would be what we call our optimization variable. Where density is close to 0, that's where our voids will be created, material would be removed, and where density is close to 1, that's where the material is present. Okay. So our entire optimization problem is essentially reduced to finding the distribution of the density, so-called density variable, and please let's not confuse it with the material density. Okay, that's like to say it is related to material density, but it's a hypothetical mathematical parameter in this optimization algorithm. And the density based, we can have a heuristic approach. I will show you in our context what the heuristic approach, how was that implemented. And formal approach would involve sensitivity analysis, that how if the temperature varies, like rather we will take energy or compliance and the minimization of that using a simple variations, and do a sensitivity analysis, and then solve a formal optimization problem using method of moving asymptotes, dynamic programming, integer programming, and so on. Most popular is the method of moving asymptotes. Recently, this level set based approach, which was essentially introduced for interface tracking in multi-phase flow, that's also gaining good attention in topology optimization literature. That the level sets boundaries which we get, those are essentially the ones which will be the defining limits of our material. And similar to density approach, people have also used phase field. These two are related. This very small difference. Somebody calls it density, other people call it as if it is a multi-phase material, and the multi-phase material again is being defined by a scalar variable, very similar to the so-called density. On-off method, as the name itself suggests, where there is a material is 1, otherwise it's 0. So it's a sort of binary representation of the process. We have used exclusively the density-based approach in our designs. Now, a brief overview of the governing questions which we took. Our focus to begin with was a simple planar bus bar. We had two sets of problems. The first one was a DC side. So on DC side, we will be using planar simple bus bars of specified thickness, because in industry, the copper sheets come in pre-defined thickness, 3 mm, 5 mm, and so on. Okay. So our focus was not on the thickness optimization, because that will make the problem too complicated from manufacturing perspective. So take standardized thickness sheets of copper, okay. And these will also be, these should be reasonably thick to ensure the stiffness or strength properties. And we took a design wherein we said both sides is open. There's no forcing here, so it would be losing heat to natural convection to the ambient of the enclosure at T infinity. So it was a simple, like this is arbitrary domain. Of course, in our application, we took a simple rectangle. In the topology optimization, we essentially start always with a rectangular type of box. The design, final design will come out of that. Okay. But general problem could have a different types, boundary conditions, Neumann boundary conditions, Dirichlet boundary conditions. Here the superscript V that represents the electrical problem, the voltages, and T represents the temperature. So in the same geometry, I have tried to put boundary conditions of both of them. And this is our model. For electrical model, we are solving what we call electrical continuity equation in terms of voltages here. So divergence of sigma gradient of P, P is the voltage or potential, sigma is the conductivity, and we know the electrical conductivity is very sensitive to temperature. We have taken a linear variation of resistivity. So rho 0 is the resistivity at the reference temperature, and we have taken linear time temperature dependence. That's how the sigma is related. On thermal side, we simply did a thermal equilibrium, so we get something similar to a Poisson problem. So these two problems must be solved in a coupled fashion by our physics solver, and we just combined them in a generic equation for developing our code so that we can develop a modular code. It could be called with the parameters which are listed here, once for the thermal problem and then again for first for electrical problem, then for thermal problem, and solve them iteratively until we reach the convergence. So this is a flow chart of electrothermal simulation. We initialize the domain, then solve the electrical problem. The potential distribution could be finite element or finite volume based code. Then evaluate Joule heating, then solve the thermal problem, then see if convergence is met. Otherwise, just repeat this process. Okay, that's small tolerances which have used for both of these separately. Optimization approach, we used a simple density based approach. One would represent material, 0 would represent hollow. But in numerical implementation, we can't go with one. One is okay, but 0 could create a problem. So we'll modify that. Okay. The material properties would be written in terms of this density theta, that our artificial density which we've introduced earlier. And this is sort of, you would use a penalization approach. Theta would be taken this theta min instead of 0. So let's say value of 10 to the power minus 3 or 10 to the power minus 4. That would be your representative of 0 to avoid the problems in numerics. And general form optimization problem is to find theta. Our objective function becomes f theta. And in our case, we are using thermal compliance, similar to what we have got the structural compliance, subject to the constants. Our constants here would be our physics problems, boundary conditions, and temperature limit. So this is a formal approach that find this theta. Theta would be for all the elements or all the volumes, and the other the problems like subject to the thermal problem, electrical problem, maximum temperature condition, and the new design should lead to lower volume than what we started off with. And theta lies between theta min and 1. In heuristic approach, what we did, this is I'll get back to this place, optimization step, that we will compute the temperature rise, find out what is the maximum temperature rise. If the maximum temperature rise already has exceeded our limit, then we have to go back, start with a bigger domain, because now we've used lesser amount of material. If not, then we'll go to the cells which are in cooler region and not contributing significantly to conduction process, and that decision will be based on the current density in those elements. If the current density is very small, that would lead to lower Joule heating. So those are the elements which could be eliminated. Their density could be set to theta minimum. And we have also got to be careful that look, we shouldn't take so that it creates a disjoint path. So that has also got to be taken care of. We should have a continuous material distribution. So that's also what ensured in this process. Okay, reduce them, ensure the continuity of the current flow, and then go to the next optimization, reach the convergence. So this is a top, sort of formal approach: initialize domains, solve governing equations, evaluate objective function, then perform sensitivity analysis or regularization, optimization step, get your densities. If converged, that's where you stop. That's your final design. Okay, I'll come to the optimization examples. We'll first, we started with a simple rectangular bus bar with two ports, one input port and a ground port, okay, with 500 mm square. And these were reference properties of resistivity and thermal conductivity we assume to be constant. For copper, in our range of interest, that's 273 Kelvin to 373 Kelvin. The conductivity of copper remains more or less constant. So our thermal problem, we have assumed constant thermal conductivity. The current density input, we took few different options available. Similarly, we also varied this convective transfer coefficient. And for heuristic approach, we have taken a simple structured grid of cell-centered finite volumes with 37,500 cells were used. And this is the result after 82 steps. So though significant reduction is taking place, that earlier initial geometry was this with 500 by 500 square, but we're still not satisfied with the temperature. So then we moved on to the formal one, and we first performed a grid independence test that what would be the minimum area obtained with different types of, with different number of elements for a given current density input. And these are the results for different current densities. So as we vary the current density, we will see that material requirement that keeps on increasing. So starting with this black box domain of 500 by 500 mm, we get optimal design for this simple bus bar. Similarly, we also, I'll skip these problems, sorry, slides. We also took an LSEPT with three ports, one input port and two output ports. And for this also, for different current densities, we obtained, starting with simple rectangular or LSEPT domain. We obtained. And then we took a multi-port. There will be different connectors in the middle here. And for this also, we performed our topology optimization with different current densities. This was our final optimized domain. Okay. And what we observed that we can reduce more than 50% of material by using a formal optimization procedure. And material requirement increases with an increase in current density input, which is just given. We all know that when we higher the current density, more material, more amount of copper we would need. And we also said that the physics is not violated because the current always, we have seen the way the designs are obtained, that as if the current is taking the shortest possible path. So physically also our designs our optimal designs appear to be sound. So I think that's what time we had. So that's where I would stop. So thank you very much. If there are any questions, please. Most welcome. Yes, sir.
Very nice talk, processing. Might be naive question, but see, because the application that you mentioned, so I'm talking from solid mechanics perspective, because temperature going to zero and then rising, zero and then rising. So
temperature going to zero.
When it is switched off.
Oh, it's not zero. Okay.
But no, not zero, but yeah, it is essentially some minimum value and maximum value. I meant to say that.
Yeah.
So in that case, it essentially constitutes a case of fatigue. So when you have very simple geometry beginning with the rectangular shape, but when you optimize it, then it has essentially some curves and so that can essentially lead to some failure related to fatigue, perhaps.
Yeah. In fact, when we submitted one of the papers based on it, this was one of the things you got from one of the reviewers, that why did we not invoke at the same time the structural analysis? Okay. But that was not our mandate to begin with, because these connectors are fairly stiff.
Yes.
Okay. And they are used, though they are on moving vehicle, but they are put in so-called relatively stationary box. Mm-hmm. The loadings, there are no structural loadings per se. So the fatigue is not that critical part here. So we discussed this when we started off. They said, no, let's forget about that. That's not really our concern. Our main concern is the temperature management.
I see.
So that's why we stuck to only the temperature part. We first did the DC part. AC part is a bit more complicated because that leads to three-dimensional Maxwell equations, where not just the thermal part, we have also need to be aware of what is known as the eddy currents, and they will lead to the fluctuating magnetic fields. So the electromagnetic fluctuations which are created, those must also be maintained within certain limits. Otherwise, the functioning of the IECs that would be affected. So that we have not yet touched upon. That would be a future problem.
Okay, thank you.
And one more question, only one question. Yeah, please.
Nice presentation. If you want to make this product, what process will you recommend, sir?
Well, that's frankly speaking is not my domain. Our brief was from the industry partner that you give me the software for our designers. So we designed a software kit and we gave it to them. Their in-house designers, they will design, and they will, of course, they will get in touch with the manufacturers. And of course, in the case of this thermal electrical connectors, manufacturing is very, very simple. They are dealing with the sheets of uniform thickness. Only thing is contour cutting would be involved. That's all.
But since that shape is complex,
yeah,
maybe 3D printing can be thought of.
No, but then for these problems, we have got a fairly thick copper sheets, minimum 3 mm, most likely 5 mm thickness for EV applications. No 3D printing. Take the material or sheets from the market, okay, and just cut them.
Okay, thank you.
Your CNC machine.
So thank you very much. Sir is available here during the high tea. I request to students who have questions, they welcome. They will discuss with sir. Definitely. Okay.
Okay, so thank you very much for your patience with me. Thanks a lot.
Please.
I would request Dr. Basant Singh Sekawat to felicitate Dr. K.M. Singh. A big round of applause. Now we are heading towards our second plenary talk by Dr. J. Ram Kumar from IIT Kanpur. I would like Dr. Basant Singh Sekawat to present a Tulsi sapling as a token of gratitude to him.
Dr. J. Ram Kumar is a professor at the Department of Mechanical Engineering and Design program at IIT Kanpur, specializing in micro and nano machinery, tribology coatings, and corrosion. He has published over 200 articles, holds 69 patents, and secured over $4 million funding. He has received several awards, including Eminent Engineer Awards, IEI India. I request Dr. J. Ram Kumar to begin the plenary session.
So thank you to Vasant for calling me. And sorry, I was supposed to come on the first day. I could not come because of my commitments. Thank you so much, and thanks to the organizing team who has put so much of efforts. So today I would try to move out of the normal track of mechanical engineering, try to get into the area of robotics, and we have started working in the domain of cobots. So I thought, let me very briefly share. So when I walk through, I would try to introduce some of the medical robotics, what is there, how is it used. And many of you would have realized during COVID, it used to be like a paramedic nurse. It used to come and deliver food, medicines. So that's been there. But we have gone much higher than that. So that's what I thought, let us look into it. Then I would like to compare what is manual and robotic procedures which are followed in the domain of medical. Then design and control procedures for surgical robots. Then design of conventional master console, whatever was there, and then limitations of conventional master control. Then we move to cobots. Then I would say design of assisted oral examination methodology, which we have started doing it. And then a few learning from the cobots, whatever we have done in our lab. So when we talk about this medical robots, they fall under three domains. One is medical devices, the other one is assistive devices, and the third one is simulator devices. Simulator devices are effectively used today because now the doctors wanted to understand what is the operation are they are going to do and how is the complexity and other things. Simulation is coming up in a big way. AR, VR getting introduced in medical field is one big area which is open for engineers to explore. And this is a multi-billion industry which is there. The other extreme end is medical devices. So there are a lot of surgical manipulators and tools which are started using it. A lot of diagnostic tools are there. Prognostic and diagnostic tools are there where robo plays an important role. But if you look at therapeutic, also robots play an important role. But intermediate phase, where there is an assistive device, there it is a green area, niche area, where we need a doctor to do the surgery, but reduces his fatigue. Today, what has happened, the medical domain, the operations have started running in for 8 hours, 10 hours, 12 hours. A dental RCTs have started going around for 3 hours and 4 hours. It's a huge fatigue cycle on the doctor. And today, the doctors, number of doctors with number of patients, there is a huge mismatch. So currently, the doctors are forced to do several RCTs today. So the first 2 RCTs go in a big way, then slowly the efficiency goes down. Accuracy slowly gets also here and there out of control. And interestingly, we talk so much of engineering in medical domain, we never talk about cutting a slot or a groove with 1 micron accuracy, 10 micron accuracy. So the doctor overcuts it and then he stitches, we say it's okay, right? But by doing so, there can be complexities or it can take more time to cure. So in that way, assistive devices is one area where we are looking forward for a lot of things. So exoskeleton is already available. and wearable devices are already available. For example, if you look at cinematic industry or movie industry, they have exoskeleton where they fix the camera and go around. To a large extent, it has a very high stability and it also has a very good resolution to control. But now, we don't have a similar thing in the medical domain. For example, if a doctor is cleaning, he repeats this operation maybe 100 times for a patient. That puts a huge fatigue. That fatigue affects his muscular disorder. And over a period of time, many of the good doctors start avoiding doing surgery. But their wisdom also goes away because of the fatigue. So here is an area, assistive devices, which we are trying to focus. And if you see number of publications, it's going exorbitantly high. So you see from 2016 to 20, a huge jump. From 20 to 24, if you plot, it's twice of the jump, whatever it is. Right. So this area is number of publications in the area of robotics alone. With respect to medical field, there is a huge scope. And the number of publications country-wise, if you see, of course, United States is very high, and our country, we are just started crawling in this area. There is a huge scope. I'm just trying to bring a huge scope in this area. So commercially popular medical robots are, these are some of them, which predominantly helps in taking X-rays, CT scans, fixing a patient for the operation, taking a photo of the patient and then trying to align the scales when the doctor stands behind a screen. All these things are commercially very popularly available. So when we talk about manual procedures and robotic procedures, the hand-eye coordination is extremely important when you do manual. Right? It's like driving a car. And many a times we don't even realize we drive a car at 100 kilometers per hour. If you want to sweep, it takes a fraction of a second. Right? And we do it so fast, our eye keeps on scrolling it very fast, we don't even realize. But when we do an operation, it's also very difficult. So hand-eye coordination is very important. It's the human limitation is dexterity beyond a certain range we are not able to. Suppose if there is a blood flow which happens by cut off a vein, it's so instantaneous, it's highly impossible for a doctor to react and then go stop it. Right? Then stable and accuracy is always very high in robot, and then real-time judgment also can help you in assisting you. Then I have talked about that. Then flexibility and adaptability in human side, it is there, but again it is limited to certain geometries. For example, if you want to do an angle behind your head, it's not possible. So there are certain places even in the head when there is an operation going on, they keep turning your head multiple times to suit their requirements. If you are an unconscious patient, it's okay. But if you are a conscious patient, if you move to a dentist, if he puts you in a wrong position for his comfort, then you are not comfortable. So that's what we are talking about. Then haptic sensing and decision making. So these are all the human expertise which are there. The human limitations I have drafted it. Then the robotics, what it can do, and then inherent robot limitations also I have done. When we start looking into design and control procedures of surgeries, you see it can fall in any of these things. So you have a master console, you can go stand behind it, and you have a joystick to operate, right? So when you use a joystick to operate, you need a haptic sensor. There are three-axis haptic sensors are not many available, and it's not so very high responsible. So you can have a master and a slave console, and people are now using it in a big way. So these are some of the design of conventional master control systems you have. So you have two robots. You have a doctor standing there who tries to teach the robots what will be the movement. So accordingly, it's a teach-learn technique or a teach-learn pendant, which is very common in industrial robotics. But in medical field, it is very difficult. Why? Because there is a limitation on the resolutions, right? The encoders, the sensors are a limitation. So the design for conventional master console is they try to have a sensor-based device like joystick. Then it manipulates slave robot in real time based on forward and inward kinematic equations. It works, and different mechanisms mapping is also carried out. But what are the limitations? It has a limitation on the haptic feedback. See, when you get into an operation or if a doctor cleans your skin, You only shout. After your shout, the doctor gets the audio sensor feedback and then he reduces the pressure. So that's how it works. But when you are doing many operations, the haptic feedback is very important. There is a limitation for it. Then the next thing is too complex to express a mathematical equation so that 100% robotics can be done. Then it is teleoperated at one point convenient, but at the cost of margin of errors. Telemedicine is good. Teleoperations are good, but it has a small after effect of it. So high operating time is compared with the conventional surgeries, and it needs really, really high skills for that. So now comes the domain of cobot. So cobot is I try to teach it and then I try to execute the same. Right? So now what has happened, it's not a moving robo, it's a stationary robo wherein which the doctor teaches and you keep your hand on the patient's hand and start learning it. So it's within a confined space, it is there, but the robo cannot work of its own, or it may work of its own, but it's predominantly operated by the doctor. So here in which we are not 100% conventional, we are not 100% robotics, we get into an intermediate domain and then we start doing it. So cobot is something which is sharing space and a lot of things are coming in this domain. So if you look at the level of collaboration and if you look at the requirement of intrinsic safety and other things, we are falling in the center domain. Most collaborative applications are in this type. So you can see they are consistent and you can also have sequential operations, whatever it is. So when we talk about dentistry, it's a very interesting field. So here in dentistry, every small thing is very interesting. Suppose you want to take a photo of your teeth, right? X-ray is one domain. X-ray is okay for a crack analysis. Suppose you want to see a growth or something, one feeding on the other, yes. But if you just wanted to see an X-ray of your mouth to find out where are the decays start, the challenge number one is you have saliva. When there is a light which hits on the saliva, it reflects. So the image, whatever you get, is not correct. Second thing, no teeth, no 2% teeth are in a fixed domain and it's not flat. It's curved and there is a light limitation. So there is a light limitation. The camera has to take a photo where there is a saliva around and the pH of the saliva plays an important role in the reflectivity and it has to take images. And then it is not necessary taking images only on the front, you have to take images at the back also. Right? So look at it, it's only one part of the start story. To assess your health, how do we use it? So here, what the cobots can come into existence, wherein which the and the other thing is today everybody is very much worried about the oral hygiene. So the doctor, what he does is he has an arm wherein which he pushes it into your mouth. There is a camera there, and then he tries to video record it or he tries to rotate it and take a photo. So now what is happening is when you do so, you try to assess the patient instantaneously and immediately. Now once that is done, so then you try to look at the course of action, what is to be done. When we start looking into the course of action, the crack is never straightforward. The crack is small, and when the crack is small, it can be superficial, it can be internal. Then you have to do a grinding operation to gouge out whatever is decayed and you have to start filling it. So when this comes into existence, it's very difficult for a 100% robot to come into existence and start doing it. So here again, the cobot comes into existence and then what it does is, it tries to have an assessment and then the doctor facilitates. So if the doctor has to fill the same part 10 times, now he does it once and then he allows the ratio, the amplitude will be reduced and the force will be reduced accordingly. So all he has to do is do it 3 times or 2 times and leave it. Then he has to just keep watching, the robo will start finishing up the job. So this is the other thing which they are looking at. A small demonstration which we did in our lab. So we had a artificial jaw which is available in the market. This is used by dentists. So we used a robo. Then we attached a camera we try to figure out how do we swing around and then take a photo. How do we open it with minimum light and take a photo? So here there is a lot of need for stretching of images and developing the photo bank. So this is an area which we are trying to work, and dentistry is one area where it's a huge demand area. So here cobot is going to be the future. So assistive cobots. And so these are some of the things which we did. We also tried doing grinding. We also grinding the teeth, removing the tartar. So all these things we did. So initially we used to teach, and then the robo will be used for doing the further operation. And then what we did was we also came up with a software algorithm where in which put your face there, it will try to orient itself for 0, 0 axis, and then it will try to take your jaw. That it will try to 0, 0. It takes a relative 2, 3 measurements, and then it knows where to go and approach. And here it is pretty interesting. The child is very small face, child is not stationary, child moves, and the elderly people have their own problem. The number of damaged teeth and is very difficult. UP there is a convention of eating a lot of pan. The teeth gets decayed so fast. The contrast is different. So all these things we are trying to figure out how can we do it by this cobot system, and we are to some extent partially okay. So this is one part of the story. So we developed a lot of fixtures, how to keep the camera, and then finding out we developed artificial saliva, coated it on top of it, multiple layers of coating.
Online camera which sees the denture of the patient, and based on that visual.
So this is what we developed, and then we are trying to look into it. And the video, whatever comes, we convert it into a photo or an image for the understanding. And the other thing what we wanted to do is, which we are also trying it along with the cobot. See, now currently when you go meet a doctor, the doctor says, okay, temperature measure karo, pressure measure karo, this, that, weight. And then he puts somebody, a paramedic, prepares the file to the doctor. A similar thing we wanted to do it for dentistry. So as soon as you go to a dentistry, there will be a system where in which they try to take a photo of your teeth and other things. So before you go to the doctor, your file goes to the doctor, and doctor assess what is that is there in your teeth or in your jaw, so that he can start working on it or he can start looking into it. So for that, we are trying to develop a standard system where in which these cameras can be done. So this is one thing which we tried doing it. And then afterwards, we wanted to have a understanding. So we did a lot of trials. We integrated ML/AL into it. I did not want to get into the equations. So it was a slow learning, then accelerated learning. So this is where the proficiency comes. So we were trying to do a lot of trials. So many number of trials such that we can get the rapid procedure learning and termination of the proficiency. So for learning, we had operating time, specific procedure, console, docking time, stepping time, all these things we were looking into it. And the length of stay metrics also, LOS, we established for it. This is one thing which we developed. So we are trying to see everything with the doctors. For the doctor, we will be able to do. Next, what we did was we wanted to reduce the fatigue of a doctor. So here in which what we did was we tried to develop a device where in which knowing the doctor's angle whatever he has kept his hands, we converted into links. And from these links, we have developed an assistive stand where in which the stand height will be adjusted. So the doctor rests there properly, and then he does only this. So he typically moves only his end effector and then does the operation rather than moving this and that. So as soon as he settles down, so if you look at it, if there is a patient here, the doctor will always sit down here and try to answer. But when he does it, many a times he does not get access to his face and to a teeth. So he stands and then does it. And then he always gets into a skewed position and he does it. Right? So now what we are trying to come up with, we put the robo behind. The robo stands here, whatever it is. The gripper stands here. The gripper will come here. So the doctor will always try to have it in front of it, and then he will start doing it. So he will be stationary. The cobot will take all the skewness. So that's what we are trying to do. We have understood the gripper. We have developed a small device. We have applied for a patent for it, and we are working very closely with KGME. So these are the novel procedure matrix which we are for measuring the learning curve. So hand tremors versus time, hand movement versus time, eye coordination versus time, and space utilization versus time. So this is a matrix we are planning to develop. It does not exist. So we are planning to develop in this domain. And then we wanted to use cobot for evaluating for oral examinations. Conventional methodologies for evaluating the learning curve in the dentistry is getting reviewed. So we have also come up with some measures and matrices for it. So the computer vision based method are tested and evaluated for learning curve in surgeons with cobots. So our focus is only more on dentistry. So we are trying to work very closely and then get more details. So this is an area which is very new, which is very fresh. Not many people are there. Robots is used in industrial applications in many areas, but for human societal aid, so this might play an important role. And here in which we are not removing doctors, we are making the doctors much more efficient and professional. That's what is our focus. So I'm done. So if you have questions, you can go ahead and ask me. And I did not present, we have put EMG sensors, measure the forces, what is the muscular load, all these things, fatigue analysis, all these things we have done, but I did not want to present everything in this. So I just thought I'll give a pre-up. Yeah, I'll be happy to take questions if there are any.
Thank you very much, sir. And just there is one request. Please visit on sir homepage. Sir has developed a very good lab in IIT Kanpur. This lab basic aim is to develop a medical. Yeah, medical devices. And medical devices, you know the level of complexity of these medical devices. He's incorporating all the complexity when he has to be a developing a device. Am I right, sir?
Yeah. And apart from it, I work with him on heat channels, heat pipes also.
Heat pipe channels also. So this is a good opportunity. I'm just requesting you. You just see what our scientists, what our professors they are doing in IITs. I visited 2 times in a cell lab, and I believe that this is one of the best lab, and not in India. Maybe in our, we say that in our.
Yeah, and we are open, sir.
Yeah,
if any student wants to come for a summer, we are open. For your full project, we are open. For a semester, we are open. For 1 year, we are open. We will give you accommodation free. So apart from that, you have to manage.
Yeah. So I'm just requesting sir. Sir is also here during the concluding ceremony. So we have a plenty of time. Take the advantage of sir knowledge. I request to all faculty members as well as students, please discuss with him. Take the advantage of his lab, his knowledge, whatever his experience. So thank you very much. Yeah. Any question? Yeah, you are. Yeah.
You said that learning. So on the fly learning might be on your cards later on. You said.
Pardon me?
So if I understood correctly, that you said for cobots, because they need to taught first.
Yes.
Right. So they need to be taught first. So, but on the fly. So when the operation is going on, then they are learning there. So real time. So that.
See, what happens is whatever you might try, you have an expertise, you always fall in the local group. And if you see many a times, whatever you do, you practice only a certain algorithm, protocol and algorithm. So many a times that is frozen. So if it is for me, when I buy a Fugu and if I it works for example, if I start writing, it helps me in writing. So my pressure, my angle, whatever it is, almost it is fixed. So for a doctor also it is getting fixed. So maybe if he does it 3-4 times, it's not okay, this is what is the next setup. However, we are not focused in completely giving it to him. We are only helping the doctor in assisting in doing a repetitive job. RCT typically takes nowadays 2 to 3 hours. Very rarely it happens very fast. Drilling of the job, it takes its sweet time. So the doctor has to spend so much of time drilling, doing. So that can be reduced. And now we are talking about productivity concept in dentistry. So what is the turnover time per patient? So that's what we are talking about. So 6 patients together, one doctor starts next. They come back next. So that's what we are talking about because we have a duct in dentistry. Oral cancer is picking up.
Yes.
The other interesting challenge, what I feel, and anybody can help me out also. See, when there is a what do you say, cancer or something which is stuck inside your mouth, right? Along the skin, it is there. So now you have to measure that fellow and assess it how serious it is. For example, if I give you this bottle width and height, you can easily measure. So here is a skin, and inside a skin it is affected. Depending upon the length, breadth, and depth, they have an index. So now you have to measure that. So that's a challenge. So many things are there which we can do.
I'll talk to you in person also because it has one parallel also what I was thinking of. Thanks.
Thank you very much. Yeah.
Sir, please.
So now I would request Dr. Basant Singh Sikawar and BP Sharma to felicitate Dr. J. Ram Kumar.
This is my
Privilege. I'm just introduced. He is my colleague also, and I think I'm just one thing to tell you. He is in nanotechnology. Actually, he is a founder of this startup, and you see, I'm not explaining everything. Is you? He is a brilliant scientist, brilliant manager, brilliant administrator, and brilliant worker. You see that without any things in his hand, he has set up a facilities where he can develop the large scale mass, develop a large scale devices, develop a large scale machines. All these things. When I talk to him, can you do? Yes, I can do, and I'm really very appreciate. And he's helping us lot of. I'm really very grateful for his helping, support, guidance. I'm asking his many committees, my department, and when I talk to him, he's picked up my phone, all these things. So thank you for coming. Yeah.
Yeah, okay. And he is the person who Vasa was done by him, Prime Minister for this.
So let's move towards our third plenary session. Now I would like to request Dr. Basant Singh Sikarwar and Dr. BP Sharma to present the Tulsi sapling to Professor Dr. Thanika Velan as a token of gratitude.
A big round of applause. For this session, our plenary talk speaker is Professor Dr. P. Thanekai Velan from CSIR National Physical Laboratory, New Delhi. The topic of his plenary talk is creating advanced materials from waste biomass and sustainable development towards energy, environmental, and lifestyle product applications. Dr. Thanekai Velan is the chief scientist at CSIR Central Leather Research Institute, Chennai. He founded the Advanced Materials Laboratory in 2016 and leads the Materials for Lifestyles product group. He holds a PhD in leather technology from Anna University and completed his postdoctoral stints at Texas Tech University in the US and Rice University. Specializing in cleaner, leather processing, and bio-based materials, he has over 135 publications, 29 patents, and numerous national awards. His innovations, such as waterless chrome tanning, have been commercialized in over 180 tanneries and led to the creation of bio-based leather-like materials for startups. Now, I'd like to invite Professor Dr. Thanikai Velan to deliver his plenary talk.
Thank you. Thank you for the nice introduction. Let me first thank Dr. Basan for inviting me to this nice campus and for this nice conference. And I thank all the organizing committee for making nice arrangements, hospitality, everything. Thank you. So let me just go into the speech. Today, I'm planning to talk on creating advanced materials from primarily the biomass waste, specifically for certain high value applications like energy, environment, and lifestyle. And I just give a little background about my talk. Just I wanted to introduce the skin. Just now, Dr. Ramkumar talked about the skin, the cancer effect, all those things. So for making leather, the skin is the fundamental raw material, and it is a protein, and there is a key protein present in the skin, which is known as collagen. And the structure of collagen is very complicated, and it was discovered by our own Indian scientist, G.N. Ramachandran, in the year 1954. And just before, a few months before, the structure of DNA was solved, he just missed the Nobel Prize by just few months. So many people may not aware about it, but as an Indian, we must know about it. So that is the reason I make this point important to every conference. When I get any opportunity, I try to share. So this man really deserves Nobel Prize, but things happen. In 1954, within few months, he missed it. So this collagen protein present in the skin is a very nice nanomaterial. It has about 300 nanometer length and about 1.5 nanometer width, and it has a triple helical structure. And if you try to look at the architecture, you have the single collagen molecule, and then it assembles parallelly, linearly, and longitudinally as well. And then it tries to form a micro or pentafibrillar structure, and then it forms various microfibril fibers and fiber bundles. And finally, you have a macromolecular skin structure, which is completely randomly arranged. It is not properly arranged at a macromolecular structure, but if you try to go into the individual fiber bundle, then you look at the fiber, then you will understand that you will understand that it is very nice homogeneous structure at molecular level. So in terms of food chain, suppose if we try to look at everything starts from agriculture, and where the animals are reared for agricultural purpose as well as for meat purpose, specifically the domesticated animals. And the reared animals are consumed for meat purpose, and the moment the meat is consumed, then you will have the byproducts, or the base product is the skin or hide. Suppose if we throw away, then obviously it will create some pollution. and it will end up with the landfill. And therefore, the leather industry try to consume this as a raw material and then convert into a fashionable material. So that is the typical food chain with respect to the leather industry, how it is connected. And I am trying to look at certain public misconceptions where some people think that the leather industry kills the animals, which is not actually correct. So I am trying to tell that the animals are killed only for the meat purpose. As long as the meat eaters are there in the world, the animals will be killed. So that is the fundamental. And some people really don't think that correctly. So I just wanted to clarify that. So as long as meat eaters are there, the animals will be killed and the skins will be available as a byproduct, and leather industry use that to convert into a fashionable materials. Just to give an indication, the global meat industry is close to $1 trillion, whereas the leather industry is just about $400 billion. So that says the actual truth. So in terms of the leather processing or the tannery, which are located in various environments, if you look at the global status, it involves a lot of chemicals and waters, but unfortunately, it leads to a lot of liquid waste and solid waste. And for every ton of skin or hide processed, it generates about 600 to 700 kilograms of solid waste. So that's a major problem. And interestingly, it has a lot of proteins, that is collagen. So there is a great economic potential is wasted. And if you try to look at what are the different types of such wastes, it contains a kind of a metal containing collagen waste, which is chromium, is the one which is normally used to make the skin into leather. Yep, a process known as tanning. So you have both chromium containing waste as well as chromium free or without any chromium also. There is some waste generated, and these are the names of the waste, like the trimmings, cuttings, all those things. There are certain applications currently, of course, majority of them are low value. They try to extract glue or gelatin, or in some cases they try to make it as a leather board and then use it as a inserts in the shoes, etc. So there is an opportunity to make high value advanced materials out of these waste. So what we have done is to use these protein waste and then try to develop nanomaterials, composites, or even biomaterials for biomedical applications. So today I'm not going to talk about the applications or the material development biomaterial for biomedical applications. Rather, I have chosen to look at only the developing nanomaterials and composites for energy, environmental, and lifestyle product applications. So in this example, what we have done is to try to take the collagen waste without any chromium, and we try to convert into self-doped nanocarbon materials for sustainable energy applications. And what we have done is to take the skin and then remove the unwanted material like hair and flesh and subjected it to high temperature treatment starting from say 500 to 1000 degrees Celsius in the absence of oxygen. So therefore, we can able to convert into nice nanocarbon materials. And the beauty of raw material is that in the skeleton, it has carbon as well as nitrogen and oxygen. So there are people who try to take the carbon nanotubes or graphene, and since it's a purely carbon-based system, they try to enhance the electrical conductivity by doping with nitrogen. But here is a material which already has nitrogen in it. So we are trying to look at the effect of that, how you can try to achieve for getting better carbon materials. So the results are here. When we see the amount of oxygen and nitrogen, we can see that the oxygen is increasing as you increase the temperature, whereas the nitrogen is decreasing at high temperature. But still, there is a amount of about 3% nitrogen still available, even carbon prepared at 1000 degrees Celsius. So these are the typical data related to Raman and XRD. We can see the typical D and G bands in the Raman spectroscopy, and the XRD shows the typical 002 and 101 diffraction peaks of the crystalline graphitic carbon material. And we also did the X-ray photoelectron spectroscopy, where we have seen that the edge nitrogen is vanishing as the temperature is going up, and the internal nitrogen, which is substituting the inner carbon atoms, are increasing at high temperature. So the pyridinic nitrogen, which is on the edge, could be converted into nitrogen gas at high temperature. That is our prediction. And these are the transmission electron microscopic pictures, which show the carbon nano onion kind of a structure, where the typical size is about 20 nanometer onions, and with the interlayer spacing which is about 3.363 Armstrong, which is slightly higher than the typical interlayer distance observed for a graphitic structure, which is about 3.354 Armstrong. This increase in the interlayer the spacing is primarily because of the effects owing to the presence of nitrogen and oxygen atoms, which we just seen. And if we try to look at the properties, it has a very good conductivity, specifically when the temperature is very high, and we got very good electrical conductivity, and it has very nice photoluminescence behavior, and it also has a magnetic behavior, which could be primarily due to the certain impurities. That is what we found. So I don't know whether this video play. Okay. So we also try to use this for the lithium battery applications, where we try to use this carbon as an anode material, and we observed very good cycling capacity, even up to 50 or 60 cycles. And this is another example where we try to use the chromium containing carbon waste and subject it to the similar kind of approach. And here we found that at high temperatures, the chromium is converted into the chromium oxide at 500 to 750. But the moment you go to 1000 degrees Celsius, the chromium oxide is further converted into chromium. That is what we observed in the XRD. And the XPS analysis shows that the chromium is present in the 3+ form. The chromium at hexavalency, it is toxic, but we are making sure that there is no oxygen, therefore it is not oxidized, and this is proven through the XPS. And this is the typical structure formed, where you have the chromium nanoparticle around 40 nanometer surrounding by the carbon layers, and the interlayer spacing is also shown here. And here again, we got very good electrical conductivity for the materials, and the magnetic properties is fairly higher, almost 6 EMU per gram we obtained, primarily because it is not just impurities, even the chromium contributes to certain magnetism, and therefore compared to the previous material, here we got fairly higher magnetic behavior. And we try to use this for two applications. One for the organic reaction catalysis, where we try to do azomical addition reaction, and then we use this material as a catalyst, and we found that the increased yield with the reduced time, the reactions can be happen. And we also use this for EMI shielding applications, and we show that very good shielding efficiency for these materials, where the total shielding efficiency, the absorption coefficient is more compared to the reflection. And in this example, we try to do the same reaction at a specific temperature, say at say 750 degrees Celsius for about 7 to 8 hours, and we found that we are able to incorporate more amount of nitrogen, which is close to about 7.5%, and we are able to form very nice onion structures. And we try to use this for oxygen reduction reaction, and we observed that this exhibits very good outstanding overall electrocatalytic activity with good properties like high current density and superior methanol crossover immunity and better durability compared to the benchmark platinum carbon catalyst. And in this example, what we tried to do is we treated a simple iron chloride with the collagen and then subjected to high temperature treatment. And here we try to transform the initial material, which is highly insulating and which is paramagnetic because of the iron chloride. And then when we subject it to high temperature, we were able to convert to perfectly conducting and highly ferromagnetic bifunctional material, where the iron particles are surrounded by the carbon or graphene layers. And we try to use this for the two applications, one for environmental remediation, where we can see that the dyes are very nicely removed within a period of say 1 hour or so. And these materials can also be used for lithium ion battery applications as an anode, and that is what's shown here. So this is an example where we tried to convert this collagen waste into a porous spongy material, which is again highly magnetic. So here we try to use the super paramagnetic iron oxide nanoparticle and then treat with the collagen and convert subject to freeze drying technique. And then we are able to convert into a very nice spongy material. So here we can see the sponges has very nice porosity, and therefore it has very good enhanced thermal stability and also enhanced porosity. And potentially this can be used for environmental remediation application as well as the biological or biomedical applications. So we try to demonstrate the biocompatibility using certain cell lines, and we show that the cells are growing very nicely without any problem. So that shows it has potential for biomedical applications. And the same material can be used for even environmental remediation applications, where one can try to use it to remove the oil and also remove the dyes. So in this example, what we try to show is the try to incorporate the titanium nanoparticle and then develop a kind of a dual purpose hybrid materials for both environmental and biomedical applications. So we initially prepare the titanium nanoparticles, which are anatase structure, and then we incorporated and then into the collagen and then develop the spongy material. And we try to show that this can be used as a scaffold for even for burn wound healing applications, where we can see that at the end of the 21st day, our scaffold has very good closure of the wound. Even for the burn wound healing, it can be applied. And this can also be used for the removal of dye. I think the videos are not coming. So basically, we try to use it for the removal of dyes as well as which one? And that's okay. It's not a problem. So it has a application for both the oil removal as well as the dye removal, and it has a very good super compressibility behavior, where we are able to go up to hundreds of cycles without compromising the structure. So the structural stability is also good. So here we try to, this is the last example where we try to use certain approach wherein we try to mimic leather and then generate leather-like materials. This is primarily because the limited raw material for the leather industry, forcing the synthetic polymer chemistries to develop materials like synthetic leathers, which are primarily the polyvinyl chloride or polyurethane based materials. The Rexing bags typically what we see, but the problem with them, when you discard after usage, it goes to landfill and it takes years, maybe 50 or 100 years to degrade. And that is where now people are coming up with the concepts of veganism or vegan leather, where they try to use the biomass and then develop leather-like materials. So here in our group, we try to develop these materials from a variety of sources, starting from plant waste, the fruit waste, and the microorganisms like mycelium or even bacterial cellulose, and also the leather or textile waste we try to use and then develop materials. So we work on different verticals, and we successfully developed two major patents in this area, and one primarily in the fruit, where we try to develop the mango based leather like material. There is a international benchmark material which is available from Netherlands, which is known as fruit leather Rotterdam, which is already mango based material. So this is our own development, where we almost achieved the similar properties and we were able to make products out of it. And a startup company, we just transferred the technology and they already put up a plant in Gujarat. The company name is Amati Green Private Limited. This is for the plant-based portfolio, where we try to use the agro waste such as the rice straw or wheat straw, where typically after agriculture the straw is burnt, thereby leading to a lot of pollution in the air. So we try to provide a simple solution for it. We try to use the rice or wheat straw and then develop leather-like materials. And these are the products made out of these leather-like materials made from the rice or wheat straw. And this is again patent filed, and we successfully transferred this technology to 2 or 3 companies. So I think already 30 minutes over. I just conclude by saying that there are various ways to convert the bio waste into useful multifunctional advanced materials. And we have shown a few examples where we try to convert the collagen into self-doped carbon nanomaterial or chromium carbon core shell materials or nitrogen-rich carbon nanoanions or the bifunctional materials or magnetic sponge, etc. And we also shown example for developing leather-like materials. And we try to demonstrate use of these materials for certain high-value applications like lithium-ion battery, or as a catalyst in organic reactions or environmental remediation or lifestyle products. So we demonstrate that the nanoscience can be potentially used to, you convert these bio waste into some useful advanced materials. So I must acknowledge some of our students, collaborators, both in India and abroad. And I thank you for patiently listening to this lecture. Thank you. If there are any quick questions.
Yes. Please give.
So,
yeah.
Basically, which property was enhanced by using titanium dioxide anatase structure you used? No?
Basically, the titanium dioxide helps in 2 ways by incorporating in the collagen waste. One is it tries to increase the degradative properties of the dyes by some photocatalytic principle. And the incorporation of titanium also helps in bringing certain elements of antimicrobial properties, for which we try to use it for biomedical application as a wound healing scaffold. So there are 2 properties, totally opposite, but it is true.
So can we use rutile structure also rather than anatase?
Yeah, it might be possible. We just try to develop based on the anatase. Rutile also we can try and then check. It is possible.
Thank you.
Yes.
Thank you, sir, for wonderful presentation and highlighting the basically how we can functionalize the material and use for different properties. So my question is, does titania size, like it depends on photocatalysis, like you have showed it like around in nanometer range. If we increase the size, does it affect the photocatalysis rate?
Yeah, typically we try to use material somewhere around 20-40 nanometer range. And suppose if we try to alter the size, we found that it improves the photocatalytic degradation rate. But mostly when you try to go down the size, it's much better.
Okay. Sir, my another question is, like you have mentioned that annealing in the presence of argon at a temperature from 500 to 1000. At around 700, you got chromate, Cr2O3.
Yeah.
What is the possible reason for that?
See, when you try to have the chromium bound with the protein, when you try to apply the heat, then there are certain chemical reactions in the presence of thermal energy would happen. The immediate product is the simple formation of chromium oxide. Thermodynamically, that is the most favorable product. But once you increase the temperature beyond 750 up to 1000, we found that even the oxygen present in this chromium slowly moving off, and then we found only the chromium metal at high temperature.
So this is due to some crystal defects or something?
Could be. So we have not gone into the details up to the fundamental mechanism behind it. Our interest more focused towards developing materials, so we did not go into the mechanistic pathway and everything.
Thank you, sir.
Okay. Okay. Thank you very much, sir. I just brief. He's working on a making a super hydrophobic surface where they have a deposit in a like a various materials. So he's thinking this aspect, like this, what is the durability, what is
Sure.
kind of this thing.
I understand.
So definitely, Ismail, if you find a good time, you can visit and you show me. Yeah,
Yeah, we can discuss
You can
maybe during the
discuss
break.
during the. Thank you very much. Now time is not allowed to more questions. So thank you all of you. Thank you. Please.
Now I'd request Dr. Basant Singh Sikarwar sir to felicitate our plenary talk speaker, Professor Dr. Thanikai Velan. A big round of applause, please.
IT is available especially for a guest. This is an app launch. For a student, this is an F2 site. So please, this is only 15 minutes. After the IT, all of you are here. Okay, so we will start our session on a time. Thank you very much. Thank you.
Good morning and a warm welcome to our distinguished guests, esteemed faculty members, teaching staff, and all students attending today. My name is Farhan Hussain. Along with my colleague Rubika Shri, are your hosts for this keynote session. We are delighted to welcome you to the 4th Biennial International Conference on Future Learning Aspects of Mechanical Engineering, FLAME 2024, organized by Department of Mechanical Engineering, MIT University, Uttar Pradesh. Today, our keynote speaker is Professor Dr. Kanmani Subbu S., Associate Professor, Department of Mechanical Engineering at IIT Palakkad. I would like Professor Dr. Basant Singh Sikarwar to felicitate Dr. Kanmani Subbu with a Tulsi sapling.
The topic of this keynote talk is investigating the fabrication limits of microfeatures in laser powder bed fusion technology.
Dr. Kanmani Subbu S. is an Associate Professor in Mechanical Engineering at IIT Palakkad. With a PhD from IIT Kanpur, he previously served at NIT Warangal for 4.5 years. His expertise lies in micro-manufacturing, laser surface processing, composite fabrications, and machining. He has published over 100 international research articles and conference papers. He is member of IEI Laser Association and ISME. He has organized multiple workshops and programs. Now I would like Dr. Kanmani Subbu to address the gathering.
Good morning to all. Thanks for the nice introduction. And then thanks to Dr. Basant for the invitation. Okay, yeah. So I'll give my lecture on understanding the challenges in fabrication of parts in metal additive manufacturing. I'm from IIT Palakkad. If you see in this slide, okay, especially this one logo, the logo is made up of metal additive manufacturing. Whereas if you see this side, there is a statue. Okay, there is an interesting story that I will tell you at the end. Okay, thing is like we have in practice, whenever students are graduating, we will unveil the statues like this. This is the first batch unveiled statue. Okay, this is related about the knowledge tree. So this is our part of the campus, which like 500 acres land area. In that only it is covers the 10 acres. If you see here, it is like beautiful campus as well as greenery. And this is the place where I sitting in my office. And this is the main part of the campus. If you see, these are the hostel blocks, and then academic block, dining hall, and then administrative block, which are now functional. As a customary thing, I would like to introduce about IIT Palakkad, more related to the academic side. In engineering, we have 7 departments, whereas in science, we have 3 departments, and humanities 1. Around there are 1,000 students. We have a master's program, 9 master's program, and MS PhD programs also. Okay. So here, since we are talking about additive manufacturing, as I said, I have shown one statue. If you see this statue, okay, you can see the size of the statue can relate with the flower pot size. So such a big thing, okay, what we have done, we have like laser scanned it. After getting a digital image, then we are able to print it. That means we are able to fabricate it. Okay. So what I'm like trying to say from this, if you have a digital image, from that you can make a product. That is one thing you're supposed to take. And second thing is, it is not only small size or a medium size product. You can make even a large size parts also. You can make out of it. Apart from that, if you have a even a product, okay, you do a reverse engineering. From that also you can make the another product. Okay, these are the things you can learn from this particular slide. To go further, when we talk about manufacturing, all of them are thinking that they remove the unwanted material. That is true. Yeah, that is a way we are able to make a statue and all. But it is not only kind of a thing, okay, that is basically called subtractive manufacturing process. Along with that, additive manufacturing process also plays a major role. And for a few more things with that, see, then formative manufacturing also. Among all 3, now additive manufacturing is getting more importance. Why means you will come to know maybe in upcoming slides. Yeah. So how this additive manufacturing comes to the industries to have to make a product. If you see this, the wasp is building its nest. Okay, what is happening really? If you see the like this animation very clearly. Okay, now it goes. It will bring the mud. Okay, it is in a spherical shape, placing on the brim of the previous layer, and then spreading across. Okay, see, most of the process we inspire from the nature and then develop it. So this is a great example for additive manufacturing too. Okay, we'll move on further. If you see that like how this additive manufacturing evolved, it started from 1983. You may ask the question, is it started from only 1980s, not before? No, it was there. But the thing is, from 1980s only, the computer also started to develop a lot. Okay, from that time onwards, now additive manufacturing started to gain importance, and then established to 7 different processes as per the ASTM standard. Okay, so why computer plays a major role? As I said already, if you have a digital image, from the digital image, you can make the product. Okay, these are the 7 processes as per the ASTM standard. Okay, we will see what is most important in this presentation. If you see over here we talks about model and prototype. Okay, so we frequently come across these kind of terminologies. Prototype. So prototype supposed to be made. That also should be made in a rapid way. Okay, then only we're able to make an actual one. For that is the purpose, we need a process which can make the prototypes very fast. That is the reason these 7 processes are evolved, which we are calling right now is additive manufacturing. But please remember, 20 years before, we call those processes called rapid prototyping processes. Okay, because the prototype should be made in a rapid way. Okay, not only that, if you see the functionality point of view, we design the products based on the need. That is true. But another thing also, there is a constraint on the manufacturing. Due to the constraint on the manufacturing, we are unable to explore the real need or real requirement of the particular need. Okay, if you see over here, for example, helmet which we are using in a daily purpose, that can be made in a single material. Okay, with even ventilation facility. Whereas whatever helmet we are using now, there is no ventilation. Ultimately, it's supposed to withstand the impact load. Yeah, now this helmet which can withstand that impact load. The problem over in general thing is there is a thing like this kind of design you can't make by any general methods, but additive manufacturing paved the way for that. If you go further, these are like it's a die with a conformal cooling channel. That means the cooling channel can be made through the shape of the cavity. Okay. Further, you can see the complexity of the parts or products they made by this process. Apart from that, in morning plenary session, Professor Singh mentioned about topology optimization. Sir gave nicely the algorithm how to optimize the topology. After that, that should be made. How to make. See, if you see, this is everybody knows it's a chassis of the vehicle. See the first one, okay, it's made up of a solid state members because manufacturing process not allowed us to have a different shapes on that. Even though there is a requirement, we need on a different shapes based on the requirement of aerodynamics thing. Okay, we are unable to make. Then now this additive manufacturing given a way, we're able to make such a 3D printed shape like this. Okay, the next one also you see this is a small bracket they are using in the roof. Okay, that initially they are using a huge amount of material and the shape had a constraint. But the 3D printing again gave a freedom. You were able to change the material as well as were able to play with the shape of the material. Okay, they reduce the amount of material also in the record. In biomedical field, see the complexity of the shape, and then it's a porous structure. Such a porous structure, making thing it's not easy. Generally, porous we think that it's kind of a disadvantage one, but here if you see, it's a main one. It is like kind of a thing. It should be dictated in a particular fashion. Okay, then only we'll get this cell culture on that. If you see that such a structures, if you want to make, additive manufacturing help us a lot. Apart from that, not only making the product, for making even for repairing the product. This is a worn-out turbine blade. So this is a turbine blade, series of the turbine blade. If one blade goes, what happens that you have to replace complete turbine. Okay, which is costly because the material, whatever you're using is very costly. That material is supposed to withstand the high pressure and high temperature environment. Okay, so now if you one blade goes, if you want to replace, obviously it is very cost involved. In order to reduce the thing, if you able to make the correction in the blade, then you can use it. But how to do that? Repairing is okay. It's like kind of attachment you can do. You weld it, one more piece you can weld it. But welding always a problem because it has gone to a fail while acting. So in order to avoid that, we have to have a kind of a method to repair with a parent material. That means the base material is supposed to taken further, have the joining with the new material. So that is possible in additive manufacturing. This is a worn-out part. After doing that, how it's look like? It's look like a single material that's like a fresh piece of the blade. Okay. If you see overall, as I said, 20 years before, these processes are called rapid prototyping, but then slowly started to use for repairing. Then finally, these processes are called additive manufacturing. And then one more interesting thing, we say 3D, because it's on principle, we'll say how we are printing the kind of things on the paper. Okay, that's all 2D printing. Now the 2D printing, you have to extrude on one side, you'll get a 3D printing. The same principle only they are adopted. That is the reason it's called 3D printing. So the name rapid prototyping slowly evolved as a 3D printing. Now 3D printing become additive manufacturing. Okay, why this additive manufacturing came to the picture? So initially I said we are making prototype only. That means we are not making a final product out of it. It's just a prototype. After that, you have to throw it out. We can't use it in any application. You can't put in use. So that is the case. Now, what is happening in a prototype, people are making an actual one, that is true. But the thing is, it is restricted with only polymer material. But now, people explore in a material side also. Initially polymer. After that, it slowly evolved to the ceramics. Now, people started to work on metal. That means you're able to do any product or a part by any of these three materials. Now people started to work on composite, people started to work on functional gradient material. So it is started to evolve in that direction also. So ultimately now this primostraces is going on the area of metal additive manufacturing. Since we are talking about the future trends in manufacturing process, I believe that we're supposed to know about metal additive manufacturing more. In that case, if you see here, there are three processes related to metal additive manufacturing process. If you see that in metal, based on the raw material, the process are classified. If you have raw material in a powder form, maybe in previous lecture, Professor Tanigavelan said that they will make a powder, correct? Okay, they will burn it and get the powder, nano powder. Okay, now you have a powder. From the powder also you can make. Okay, only one thing you have to, here ultimately you have to get a product out of it, a part out, a shape out of it. A powder form, it's a solid, again convert to be a solid. How to convert a solid to solid? You have to add binder, compress it and get. That is a one way. How they are making puttu in a conventional way. Now another way, how to make it, you just melt it, okay, get a shape out of it. Whatever shape you want, you make it as a cavity and do it. That is the way casting goes. But here, I don't have a time to make a cavity and all. I have to control with the heat source, melt and solidify and get the final product. That is the beauty of the process. So based on the product, it can be classified. That means raw material I'm talking about. And then heat source, laser. The laser such a pointed heat source and then highly intense and directional. What I think is I can control, okay. So now we don't have a presenter. If you see the presenter, it has a laser pointer. Okay, wherever I want, I can direct it. So the laser can be used for that purpose, like electron beam, electric arc, friction, plasma, it goes. And then how you are supplying the material, that is called feedstock. Okay, so these are the few examples for the metal additive manufacturing process. Okay, in this talk, I will just concentrate on laser powder bed fusion. So what does that mean? Like here, the process is take a powder, spread on the platform. Okay, now take a heat source, that is a laser now. With help of the laser, you start to melt the material and allow to solidify. Then you will get a final product. This is the overall process. That is only called powder bed fusion because you spreaded the powder on the bed, platform called bed. Then with the help of the laser, you are fusing it. That is why the name of the process called laser powder bed fusion. If you see, yeah, this is the process you can see over here. Okay, powder spreaded on the platform, heat source comes. Once spreaded on the platform, it should be ensure that leveling of the powder is proper. Okay, so now it goes. This is the way its leveling can be done. The roller goes front of the powder and then it will level it. Okay, spread and leveling is taking place right now. Now laser source comes. It started to make the product. It's a layer by layer process. Additive manufacturing basically a layer by layer process. Okay, if you have a CAD model like this, then you can make a product by this process. After that, you have to remove the powder because which are some like unnecessary things. Finally, I need a product. Okay, fine. Now, since we are talking about laser powder bed fusion process, is a layer by layer process. Okay. When I want to make a layer by layer process, I have to first make a first layer. Am I right? How to make a first layer? There the question goes. First layer, if you want to make one track first. We say tracks. One line you have to make. If you want to make one line, how to make? First you put a dot. The dot become a line become a layer, layers become a final product. This is the overall idea. If you see here, okay, this is a machine we have in IIT Palakkad. Okay, it's a metal additive manufacturing machine, laser powder bed fusion type. Okay, this is only we discussed in the previous slide. If you see here, what is happening that we start with a single track. One single track is over, series of single track is supposed to do on a same layer. Once it is done, you will go layer upon the layer. This is the way the process works. Now, when I want to work on this single layer, how the things are like. This is the image captured while doing the process. Okay, if you see here, there's a powder spreaded on the platform, then the laser source goes from left to right. Then this green color line, which is encircled over there, that is a melt pool. The melt pool also slowly moving because the laser, whatever you're using is a high power laser source, you started to move like this on the powder. What happened that it melts the powder and then slowly moving. Whenever it is moving, it is dragging that molten metal also. Then if you see that animation very clearly, you can see that there are some powders are like spattered around the things. Can you see the spattering of powders here? Sorry. Here. It is spattering. Whereas if you go down this side, back side, if you see, there are some like powder particles attract towards the melt pool. It's an interesting physics. See, unless I'm not characterizing to this level, I can't understand like or can't make a single track with a less defect. Okay, let's see further what are the things are affecting this. These are the process parameters generally we are using for laser powder bed fusion: laser power, scanning speed, laser spot diameter, powder size, and layer thickness. Okay, the combination of laser power and scanning speed gives laser energy density. What is the role of this laser power and scanning speed? Okay, consider this a laser source. Okay, laser source, say 1 kilowatt laser I'm using, for example. Then I'm just slowly moving like this. This is scanning speed. I'm slowly going, whereas another time I'm going very fast. Now, each and every particle, based on the scanning speed, it will get a different amount of energy. I hope you're able to understand that. Am I right? So now I have to play these two parameters together how it is influencing the process. That is why this laser energy density comes to the play. I can know effect of laser power separately, scanning speed separately, no problem. Processes are well established. I can do. But the thing is, the combination of these two parameters, how it is affected, that should be known. That is why the laser energy density comes to the picture. When you see over here, okay, the track morphology, okay, so that if you see this thing, like laser energy density increasing from A to E, okay. When you see that, if the laser energy density is very less, there is no track at all. Whereas if you go little more, it is giving a defects like balling defect. I need a supposed to have a continuous deposition. Instead of that, deposited but like a balls. Okay. Then I'm getting a thick and stable. This is the required single track. Whereas the little more goes that laser energy density, then it will give a irregular shape. And finally, I'm getting a thick one. So this third one, that means C, thick and stable, and then last one, too thick, more or less good. But the problem is when I need a accurate track, I need thin and stable, not a thick one. So this decision you have to make first. Once it is done, okay, when I'm seeing from the top, track is continuous, thin and required dimension we are able to make. But how about the bonding? That is plays an important role. So now you see here we varied scanning speed for the constant power. When I see over that, this is only the top view of the deposited track. When you see the cross-sectional view of that, you see that is the interesting thing. In one case, it is like half is there within the substrate. That means bed, remaining half is there on top of the bed. Here, 1/3 of the things only there in the bed. Remaining 3/4 of the deposited track is there outside of the bed. Whereas here, it is completely not in the contact with the bed. Not only the dimension, I want to know how it is having a bonding with the previous layer. That should be known for me first. So here, if we go with say high scanning speed, okay, we are able to get only this kind of thing, which is not even having a bond with that. When we go with the low scanning speed, we're able to have a proper bonding with the previous layer. That means half of the track is there in the bed, remaining half is there in the top of it. Go further. So now they understand, okay, we are able to make a single track with less defect. Okay, good. But will it sufficient for making a product now? That is a question comes to the mind. But generally, no. Why? It is like a layer-based process. But when you want to make a layer, you made only one track only now. But the one track optimization never going to help you to make a common parameter for printing the whole product. What should be done for that? Because when you do like that, one track is over. When you come to the next track, that time some other parameter, set of parameter will have an effective role. Then one layer is over, another layer you are making on top of it. That time another set of parameters will give a better result. That means whatever you have used now, that is not an optimized parameter for the making a product or a part. Then what should be done? Then we build a strategy for that. This is called single layer, single track. This is only people conventionally do. That is not sufficient. Only we are able to convince the technical committee. Then we go further. The single layer and double track should be made. So optimization should be done for that also. Because in a single layer, if you want to make, you'll deposit track adjacent to the track. That should be optimized. On top of it, you have to do a third strategy also, double layer, single track. That means one over another, then only we will get the point idea. If we are supposed to optimize a parameter for all these three conditions, then only we will be able to get a proper product. So that is our proposal for the work. And then we plan the experiments based on this build strategies, and we are able to make like this. So here we varied the laser's power as well as we varied the scanning speed, and then we are trying to find out where in which we are getting the thin and uniform track deposition. If you see in this area only, we are getting the thin and uniform deposition. Okay. Apart from that, this side, if you see that we are trying to see the bonding of the track deposited layer with the previous layer. In that, this is the area we are able to get the thing. So these are the two set of parameters will helping us to know, okay, which area is good. Then we further continued our optimization, moved further. Single layer double track we have done. Here also we are able to find which set of parameters giving a better result. Okay. Okay. Then we have to go for the another double layer single track. There we are able to find out the like which set of parameters are giving a good thin and uniform track. Okay, so now all those things we able to find out which set of parameters are optimized for making a better part by laser powder bed fusion. And then if you see the melt pool characteristics also we are like discussed, that is published in the paper. Maybe I can show the paper at the end. You can refer it. Here interesting physics are there, but since there is no time, just I have to conclude within 5 minutes. I'll go further in that. Then here, if you see how this laser power and scanning speed, which is primmost parameter, when I consider a track width, laser power plays a major role. Whereas remaining things, if I can consider about bead height, okay, scanning speed plays a major role. So this kind of outputs we got from our experimental work. And then finally, if you see, after applying all these three strategies, we found this set of parameters only giving you the best results for making the part. Okay, this is only I have done for a single track. Okay, fine. Whether it is sufficient to make any complex products, because additive manufacturing meant for making a complex chip product. In that is a case, single track means it's a linear. Okay, if you want to make a 3D thing, it is a combination of linear and curve. So then this kind of optimization should be done for a curved substrate also. When you go for different angle of curvatures, you see for a 30-degree, more amount of material deposited over that. What could be the reason for that? The problem is what happens that here your powder is stationary. You are taking a laser and then passing it. Whenever laser taking a turn, that time what happened? It stops for a moment. That means it decelerate again accelerate. That time what happens? Whatever laser comes, it will come. You can't stop the laser. There more amount of energy went and then melted the material. That is the reason, especially in the bend. Okay, you will have more amount of material. So that should be optimized. How to optimize? There are many ways. One way is you can do optimization in the laser power itself. It's like adopting the power based on the requirement. That can be done. But for that, we have to develop a machine in a different way. So now out of these different angles, we found in all the angles there is a problem. But the primmost problem with the 30-degree, because the turn angle is very small. So there a lot of amount of material is deposited over there. That is P. So from these two works, we are able to now make the a proper track with the help of the linear as well as the curved optimization methods. Okay, that is okay. Overall geometry optimization we are doing, but what we supposed to do, we have to do a other set of work also, in the sense we have to know internally how the materials look like. Is it defect free? There is no material defect free. There is a defect. What we are trying to do, we have to reduce the defects as much as possible. In additive manufacturing, these kind of problems are most prominent. One is delamination of the layer, surface roughness, and then this support structure failure. All those things we supposed to look into that and work it out. If you see this, all these things are main reason is one is porosity. When you say porosity, you can see this a captured video while doing a process. There is something is leaving out here, blue color, white color thing. Yes, here. Then you see the further goes here. That means on a powder, laser goes, molten metal also moving further. So these are the things leaves as a pores in the deposited material. In the see the depth how much it is. It is the depth is around 200 micrometer down. Okay, if it goes like that, what happened that it will leave the pores in the material. Then getting such a good product is little difficult. So now whenever you do optimization, apart from the geometrical optimization, we have to do optimization based on this porosity defect. I'll go further. Not only the porosity will lead to a lack of fusion also. That kind of defects. Okay, if you have a pores, okay, that problem is crack initiate and fails very fast. So that also we supposed to consider and do that. And then whenever the solidification is happening, there also shrinkage error comes. The shrinkage error also leads to a pores, that is called shrinkage pores. Now this optimization should be done based on geometrical aspect as well as defects aspect. If you go further, this is the area for given scanning velocity and source power. What you're supposed to do, this is the set of parameters will give a full dense product. This is a process mapping development. Okay, for any process if you work out, you're supposed to do this process mapping development. That will give a lot of idea. Okay, since the time is very less, I would like to conclude now. Okay, I'm just skipping these slides. I don't like to go. Yeah, this is a thank you slide from the, as I said, this is the statue, or we say crucible, unveiled when the corona time students have graduated. If you see this crucible, I can see that this corona testing, online education, all those things. So people made nicely. Okay, with this, I'll wind up my lecture. Thank you. If you have any questions, please. Yeah, please, sir. Just a minute. Yeah.
Okay, thank you, Prof, for the interesting presentation. We are doing as well in this area, but we are using direct deposition method, which is electrical arc.
Okay.
Okay, we found that the most I could tell is issues lah in metal additive manufacturing, especially is is only produce near net, not net. Means net we require post processing.
Yes.
Yeah. So how you deal with that in this, especially in your research, especially. Thank you.
Okay. Yeah, fine. So this see the post processing. There are many kinds. Okay. One is we'll do the post processing for improving the properties. For example, see this problem with this additive manufacturing. It's a layer by layer process. That heat history, if you see each particle on the material, what happens that it will subjected to heating and cooling cycles several times. Because of that, the property is not uniform. It is anisotropic in nature. So in order to improve the properties, people go with the heat treatment. Okay, to have a consolidated things, they will go for heat. This is the one way. And another set of post processing is in order to get a good surface finish on the product, people go for a finishing thing. So in all the cases, if you want to do best you have to do the best process parameter optimization by doing like this for a geometrical and then defects inside the thing. Once you have done, there itself you will try to achieve more or less, as you said, it's not near net shape you try to get. Okay, so not a net shape, near net shape. Okay, after that again you have to go for a post processing. But the post processing is supposed to be not in the way that it should not change the shape. Okay, for example, you can do surface finishing process by machining also. Okay, but the tool depth, the tool diameter limits your feature machining. Okay, so now that kind of thing you should not adopt. You have to go for a generalized polishing process. Okay, instead of the tool-based polishing process, you have to go for say AFM, abrasive flow finishing, or electrochemical machining. Like that, toolless process you have to go. So that whatever shape you are getting, that shape should not be distorted much. Okay, but the post processing you have to choose in such a way that which is easy for doing the process. I used to say to all, we studied a lot, but we don't have any selection criteria. As a teacher, we are also teaching in the class. Okay, for example, harness tester is there. We are talking about many harness testers are there. Okay, we never ever teach what is the selection criteria for harness tester. Is there anything like there, like okay, which are like when you want to check the harness, which tester should be used? Because Rockwell, Brinell, Loop, there are many, correct? So we have a constraint. I'm not denying it, but not a based selection criteria. So thanks for the question. So now we are supposed to have, since it's talking about a near net shaping process, what we supposed to do? Okay, we just have a criteria or selection criteria kind of thing. Oh, if your product like this, these are the process supposed to be taken, not more than that kind of thing. I hope I answered you. Thank you.
Any more questions?
Thank you. Thank you.
Thank you. So I request you the
Thank you, sir. I would request Dr. Basant Singh Sikarwar and Sir Kumar Sambhav to facilitate Dr. Kanmani Subbu. Before starting the next keynote talk, I would like to introduce the session chair, Dr. Kumar Sambhav, Uttar Pradesh Institute of Design, Noida. Now I would request Dr. Khushbu Yadav to present Tulsi sapling to Dr. Kumar Sambhav as a token of gratitude. Now moving forward to the next keynote talk. For this session, our keynote speaker is Professor Dr. Basant Sikarwar, MIT School of Engineering and Technology, MIT University, Noida. I would request Dr. Kumar Sambhav to present Tulsi sapling to Dr. Basant Singh Sikarwar as a token of gratitude.
Professor Dr. Basant Singh Sekarwar sir is heading the Department of Mechanical Engineering at Amity School of Engineering and Technology. He has completed his postdoctorate from Iowa State University, PhD from Indian Institute of Technology Kanpur, and MTech from IIT Roorkee. His research interests involves thermal energy storage, energy systems, and modeling of blood flow and flow visualization.
I would request her to address the gathering. Thank you. Thank you very much for nice introduction. These are my students. So can you PPT? Yeah. So thank you very much. Especially I'm thanks my guest to listen me. I'm talking today about the fabrication of wettability gradient on aluminum surface using a plasma etching for generating the butter. So as you in my topics, I'm more or less discussing about how we have to fabricate the surface which has a wettability gradient. This is the outline of this presentation. So first I am talking about the detail about my lab. Some people already visited, so they know about. Then I talk about the motivation of research. Then I will talk about the surface wettability. Then effect of the surface wettability, like rate of condensation, water condensation. Then I'm talking about the morphology of the condensing surface. Then I'm talking about the droplet texture and rough surface. Then I'm talking about the methods which we are using for fabrication of a wettability gradient surface. At the last, there is only one slide, device development. I'm not talking too much device development. Then finally, I will conclude my talk. So this is my lab. So if you see in a lab, we have a plenty of facilities, especially for a simulation as well as the experimental, where we have to be fabricate the various type of a surface. Our more interest for a metallic hydrophobic surface, because we people are using this surface for producing the water in a various environmental conditions. So in my slides, if you see, we have the surface fabrication facilities, water vapor condensation unit, customized goniometer, condensation visualization facilities, droplet motion visualization facilities. We also develop the various cooling units, plasma etching facilities, chemical vapor deposition. We have on CFD solver, finite volume CFD solver. Yesterday, Professor Amresh Dalal discussed about this solver. So this is the next extant version of this solver. Then we have on droplet condensation code. Then we have the ultrasonicator facilities. Here you see that there is some images of the labs. So why we have to fabricate the wettability gradient surface? You think about now our country, they are going to be a set up the space station in a space. And you know that for survival of the space station, we need a water. And how can produce the water? If there is a microgravity. So if you see, so you know that if you have in a space stations, like we have a water source, like humidity of the air, because inside the cabin definitely there is some humidity. Then we have a urine, we have the vestige, and so many things. We have the source of water. So you can see here this slide. For survival, we need a source of water. So humidity, like wastage of water, urine, then your daily usage water, all these are the source of produce the clean water. So what we have to do here, we have to be condense these water vapor which is present in air effectively and efficiently. So that we have to be minimize the cost of the water. Otherwise, if you have to bring the water from the Earth to space station, the 1 liter water cost is approximately 1 lakh rupees. So if you have to be produced here, because we have so many, now the question is arise, how can produce the water more effectively and more efficiently? Because if we produce the drop-wise condensation, then definitely there is no presence of microgravity. So now the question is, how can produce the water in a microgravity? So that we have to be a basic challenges for us to produce the water in a microgravity systems. So this slide is tell us what is the surface wettability. So surface wettability is nothing. This is the simple example. So you already showed previous presentation, yesterday presentation, where Dr. Ranjan is explained when you putting the water droplet on a surface, there is a 2-3 conditions. Maybe a water is spread, it form the contact angle 0, maybe a water in form of spherical, or maybe a water form of a hemispherical. So according to, we have to be defined a contact angle. So here you see that the surface wettability, we say that theta is equal to 0, means the droplet is spreading. This is called super hydrophilic. If the theta is close to 180 degree, this is called the super hydrophobic. Generally, super hydrophobic surface, the contact angle more than to 150 degree. So here you can see this surface is a, I'm say that the higher wettability, and this is I'm say the lower wettability. When the water vapor or maybe most air flow over the cold surface, the surface is a hydrophilic. It condenses in form of film. You can see here. If it is a hydrophobic and the surface temperature below than to a dew point temperature, then it form a droplet, and this is called drop-wise condensation. This slide you see that drop-wise condensation, the heat transfer order at least 10 times higher than your film-wise condensation. So that's why we have to be prepared the drop-wise condensation for producing a water for more effectively and more efficiently. So this may be a, this video is not running. Yes, now it is working. So you see, so drop-wise condensation is, there is a initial nucleation on a surface, then drop is grow by direct condensation, then coalescence, then slide off. Clear? Because of this slide off, the drop is frequently slide off on a surface. This is in a gravity. So drop is in a vertical surface, drop is slide off due to the gravity. So because of the gravity, there is a automatic refresh. That's why the heat transfer coefficient of drop-wise condensation at least 10 to the high 10 to film-wise condensation. So overall, drop-wise condensation only occurs when there is a more effectively when there is a gravity. Suppose there is a microgravity, how can make a drop-wise condensation more efficiently? So that is, we have to be making the wettability gradient surface. So this slide is tell us all these things we have to learn from the nature. Professor Sabu already explained the things more detail. So nature tell us many things. How can survive in a harsh and hard conditions? So you can see here, like this is a beetle. This is the you see that flowers, leaves, all these things. They in principle is a hydrophobic. They have for survival in a harsh condition. So they tell us the why this surface is hydrophobic, because they have a microstructure kind of roughness. This is called hierarchical roughness. Means the nanoscale roughness superimposed on a microstructure kind of surfaces. So here, sorry. Okay. So here you see that the drop on a rough surface. Basically, you see that if the surface is initially surface is a, or I'm say that smooth surface is a hydrophilic. If you produce the roughness, it become a your hydrophilic surfaces. If there is a smooth surface is hydrophobic, you produce the roughness, it increase the hydrophobicity. It increase the contact angle. So you see there the effect of roughness. And there is a 3 stage of the drop in sitting in a your structure surface, microclay surface. The first stage is like a complete wetting. The second stage is a partial wetting. This is a partial wetting, and this is you see that your kind of a drop air setting. There is no any kind of a wetting. So because they have on advantage and disadvantage on these surfaces, so we prepare the partial wetting surfaces. Here the partial wetting surface, what happening in this type of a droplet sitting on a partial wetting surface, the rate of heat transfer through droplet is very high. So these are the all I'm say that expression which is available on a books, where we can find out the contact angle on a droplet sitting on a texture surface and droplet sitting on a rough surface. The another here you can see that when the droplet on an inclined surface and it is deformed, the leading side angle become an advancing angle and trailing side angle become a your receding angle, and difference of advancing and receding angle is called the contact angle hysteresis. The contact angle hysteresis play the role when we have found the retention force. Retention force is nothing when we have to incline the force. So it provides the resistance against the motion. This force is called the retention force. And droplets is slide when the retention force is overcome by the one component of the gravity. So generally we have to prepare the low contact angle of hysteresis, because we have to be remove the drop slide very fast from the surface. So here I am giving the what is the mean of gradient surface. So your surface is here you can see the lower wettability, here is the higher wettability. So what happening if drop is here, because of the passive force, the drop is sliding to from lower wettability to higher wettability automatically, passively. And this type of surface is called wettability gradient surface. And this surface has a by nature has a passive motion of the droplet. So it is a kind of a self cleaning. And here I am giving the free body diagram where you can find out what amount of drop is sliding and what size of drop is sliding from the surface. So here we don't need a microgravity. So drop is sliding by the passive action of the surface. These are the various methods which is available. People are altering the morphology of the surface. Morphology of the surface means people have to be change the roughness, so that they have to be change the wettability. One is taxing and etching. Second is a coating of low energy metal. In a taxing etching, there is a two types: the physical etching as well as the chemical process. So we are generally using the all type of methods in our lab, but for this method we are focusing on a plasma process, hot water treatment, and plasma depositions. But we are exploring the all methods. I am not discussing too much more detail about the methods, but we have to be doing all three methods, combination of these three methods. One method is not sufficient to making a wettability gradient surface. So generally we have to be making the combination of the surfaces, combination of the methods for making a surface. This is the plasma etching facility. This is available in our lab. So this plasma etching has a etch the surface as well as the deposit the metallic surface on surfaces. So one we have to be develop the how can develop the wettability gradient surface. So this is you can see this is the schematic diagram. So we have polished the this is we have to be do the wettability gradient on an aluminum surface. First we have polished the aluminum surface, then hot water treatment. Hot water treatment is nothing. We have to put the surface in a water which temperature 100 degrees centigrade for 2 hours. So what happening? There is a porosity oxidation form is one, and when dry, then we mask the surface. We have masked the surface nothing. We have put the tap. Then we have to cut the with mechanically and manually cut the strips, small and leach up. Then this type of then we have to be this do the plasma etching. So plasma etching, then we have to be remove this. So what happening by the hot water treatment? These where the tap, these are the hydrophilic, and when there is a plasma etching, this become a hydrophobic, and you can see there. This is the polished aluminum smooth surface. The contact angle is I think laser is not working. Yes. So you see here, this is the polished aluminum surface. The contact angle is close to 60 degree. After the hot treatment, the contact angle is 20 degree, and this is the plasma etching. So contact angle is 140 degree kind of. So you can see we do the condensation experiment. I'm not here not explain the experiment, but what is you can find out here. Wait, just a minute. So you can find out what happening where the surface is hydrophobic. There is a drop formation, and hydrophilic there is a film formation. And because what happening, the drop is at the interface, it is sucked by the wet-utility gradient to a hydrophilic region. So it is automatically clean the surface for the new condensation. I think this video gives the complete picture for you. You can see here. So what happening? So you drop is formed at a hydrophobic surface. It is pulled by the hydrophilic surface. Then this is a slide of kind of this term. So this type of pattern generally we get from the your surface pattern surface. So now how can predict the unidirectional wet-utility gradient? So what we have to be alter here. So this is the I'm say that the holder, and this is basically this is the cover on the substrate, and this is a target area, and here we provide the motor. This motor is rotated to move this cover slowly away from the surface. So what happening? It is exposed in your like a where there is a ions is coming and stack on a surface. So in this way, when we have to do the like a contact in roughness, we measure the roughness. So this is the order of roughness we can get here. And when we measure the contact angle from this towards the unidirectional hydrophobic to superhydrophobic surface for 40 mm surface every 5 mm distance. So these are the contact angle we can get here. So 5 mm we get a 180, then 10 mm we can get a 121, then 15 mm we get a 127, 20 mm we get a 130, 25. All these contact angle we can get here. These are the condensation pattern on a unidirectional wet-utility gradients. So you can see all the drop is shifted from your higher wet-utility sites. These are the some experiment we have carried out on a wet-utility gradient surface, inclined 5 degree and horizontal wet-utility gradient surface. So you see that the droplet radius versus droplet frequency. Here you see that the wet-utility gradient has a small droplet radius and a higher droplet frequency as compared to the inclined and horizontal surface. Here you see the area of coverage versus your have to be percent of area. So you can see that the wet-utility gradient has a low area of coverage, means it is more and more surface is available for formation of the drop and nucleations. This is the setup we have to be developed where we have to do the condensation experiment. So these are the cooling unit. You can Peltier coolings like this, all these things you can see here, and these are the
present over here is the device in development by our department. This particular device also won for Best Innovation in Technovet 2024. Now the device's name is Moisture Condensation Device. This is the basis of its working. The principle is the flow of moisture through the system. The condensation chamber has an aluminum plate which is cooled down via use of these two heat sinks, and the cooled plates allow for the dehumidification of air, and we start to form droplets over here which is collected downwards over here and further collected into a measuring bracket through these blue tubes. The rest of the air is then ejected outwards through the use of this exhaust fan. The device is very pragmatic in nature, essentially made for solving the water crisis that is present in India particularly. By harvesting water from the air, we are increasing our resources.
we are planning to set up this.
Present over here.
So we are planning to we have to be set up this device in a space station where we have to be trying to produce the water, and this is the all data performance of the device, this variability gradient. So you can see that in July, August, September, the relative humidity different, temperature different, then what is the power consumption and what is the water generation, 2.5 liter per hour, 1.7 liter per hour, 2.2 liter per hour, kind of these things, different conditions. So I'm concluding here my talk. So this study is fabricated for pattern of unidirectional variability gradient as well as the pattern surface. Variability gradient enhance the condensation on engineer surface by fabricating the continuous condensation, remove the hydrophobic surface. Droplet velocity depend on the surface variability gradient, allow the micro droplet slide towards the more hydrophilic surface, and variability gradient result is higher overall transport coefficient compared to a non-graded surface. Durability scalability remain a concern. We are working on this area because we generally found that the surface is not durable, and this research is going on, and we have things. This continuous transfer, the removal process increase the overall condensation rate and making it suitable for a space applications. These are our collaborator, Professor Mulidhar from Indian Institute of Technology, Kanpur, and Dr. Mukesh Ranjan is from Institute of Plasma Research, Gandhinagar. He is helping us for the fabricating the plasma, all these things. Dr. Sumant Upadhyay is a faculty in nanotechnology department. His wife law is a chemist, so he's helping us to some chemical process, all these things. And we also acknowledge and thanks to BRNS and SERV for providing the fund to carry out this work. For this work is Apurva, you know the video of this. Ismail is here, he is a PhD scholar. And Subham Dhawan is a graduate student, he is doing some simulation, all these things. And thank you very much. Thank you. If you have any questions, please.
Thank you, sir, for a very interesting presentation.
Now I would request our session coordinator, Dr. Pallav Gupta, sir, to felicitate Basant Singh Sikarwar. As proceeding towards the next keynote session, our keynote speaker is Dr. Ajitendra Singh Parihar. I would request our session coordinator, Dr. Pallav Gupta and Professor Dr. Basant Singh Sikarwar to present Tulsi sapling to Dr. A.S. Parihar as the token of gratitude. Dr. A.S. Parihar is a scientist, DMSRD, DRDO Kanpur. He has an experience serving as a scientist at DRDO for several years and has been credited with the development of an indigenous lightweight bulletproof jacket for protection against highest threat level 6, marked by the Bureau Standards of India. He has received several awards for his commendable work in the field of mechanical engineering. I would request Dr. A.S. Parihar to address the gathering.
Thank you very much, Dr. Basan sir. At the outset, my sincere thanks to organizer FAME 2024 and also my director, Misadi Kanpur, who has nominated me to give a lecture on the ballistic material. So, with the basic introduction of the type of the material that we are using for the personal protection, as we all know that there is a never-ending war between the researchers who are making the bullets and the researchers who are making the bulletproof jacket and the protective equipments. So here the material plays a very important role. So when we just go back to the 40 years back, when hundreds of the years back, the main theme of the production was based on the steel armor, which was having the aluminum or steel or the engineering material. So that armor made of the engineering materials was extremely heavy. And nowadays, since the performance of any type of the personal protection like the bulletproof jacket, etc., so the weight plays a very, very important role. So now we are having the, in general, two types of the material that are being used for making the bulletproof jacket and the ballistic helmet. One is the composite material and other one is the ceramic material. So the basic idea for the designing of such a system is that since all the bullets now we are encountering, they are having a high hardness steel core. So due to which the basic principle of design says that the strike face with the bullet should have the hard surface, and the hardness of that surface should be more than the hardness of the hard steel core bullet which are there inside the bullet. So the ceramic material are being used as a strike face for making the panel of the bulletproof jacket, and then we are having the backing composite which are made of the lightweight fiber reinforced plastic composite. So uh, here you can just see one of the this picture where the bullet is striked at the ceramic face. So the ceramic plate is bonded with the backing composite which is made of the polymeric. So you can just see the type of the fragmentation and the type of the cracks that has been generated to the ceramic. So these are the different type of the ceramic materials that are being used nowadays. So right from starting from the top, like from the steel, and then the people have used the alumina. Then the people, when we are in this table, we are going down, the density is going to decrease. So the lightest ceramic material that are being used in the present scenario is a boron carbide. So we are having the three grades of the boron carbide that are being used for the bulletproof jacket application. So one is the orthos boron carbide, other one is the reaction bonded boron carbide, and the third one is the pressure centered boron carbide. So and this ceramic material are bonded with the backing composite. So these backing composite are either made of this aramid based composite, which is also called the Kevlar as a DuPont trade name. And we are also having the backing composite, which is a special grade of the polyethylene material, which is called the ultra high molecular weight polyethylene. In short, it is called UHMWPE. So the main beauty of this ultra high molecular weight polyethylene prepreg based composite is that the density of this composite is very less. It is 0.97 gram per cc. So this shows that this is the lighter than the water. If we made the composite panel using ultra molecular weight UHMWPE material, so we have thrown the water, so this will float. So this is the special type of the material, and this material is being used with the backing of the ceramic. So these are the few type of the fibers based composite material that are being used from the last more than 25 years. And the best, the green color row is there. So there are the various grades of the UHWP based fibers. And now in India also, few of the industries, they have started making the for the prepreg. So here the concept is like this. By the gel spinning process, we are drawing the fibers of ultra molecular weight polyethylene, and then this ultra molecular weight polyethylene fiber are embedded into the form of sheet, and then this sheet is made by the compression molding, which is a 090 So this is called the UD prepeg, unidirectional prepeg, because in the woven this composite, we observe that there is always a crisscross pattern in the composite. So one is the warp and the other is the weft. So due to the crossing of the fiber at the intersection point, that creates a stress concentration point, and that deteriorates the strength of the composite. So this is the reason that new technology was adopted, where the fibers are embedded into the matrix. So here the matrix is in general two types of the matrix. One is the polyurethane based matrix, and the other one is the styrene butadiene, which is the SBR rubber matrix. So these fibers are embedded into the matrix, and then a sheet is formed. And then on the basis of the how to make the composite, so 090 layers are pressed in the form of laminate. So here we are avoiding the crisscrossing of the fiber. So due to which we are we are increasing the probability of the fiber to be utilized for their maximum strength. So this is the new technology, and this is also called the UD technology. This is the unidirectional technology. So there is no crisscross of the fiber. And these are the some of the basic details of the ultra molecular weight polyethylene. So starting with the high molecular weight, we call the polyethylene. Then we are doing the polymerization reaction, and then by the gel spinning process, we are making the fiber spinning. So this gel spinning process, here the molecular weight of this polyethylene is more than 5 lakh, and then by the gel spinning process, and then gel spinning is ultimately a state of art technology where the fiber has to spin through the spinnery, and then some stitching and all those things are applied. So here, what the strength of the fiber we are getting is in the order of 3.5 to 4.5 GPa, which is a very high strength fiber. And these fibers are now embedded into the matrix of either polyurethane or the their matrix, and then we are converting it into the UD sheet. And then that UD sheet is made in the form of a composite by using the compression molding. So this is the entire process. So up to year 2010, these ultramolecular weight polystyrene hard armor panels they use for making submersible panels. But after year 2010, now the researchers who are doing the research for making the ammunition and the bullets, so they have increased the hardness of the bullet. So now the high hardness bullet they used to come. So the hardness is in the order of 50 to 60 HRC. So in order to stop that bullet, this alone alpha molecular weight polyethylene composite is not able to withstand those bullets. So this is the reason that we are using the ceramic as a front facing, and this is the one of the photo of the bulletproof jacket which University Kanpur has recently developed. This bulletproof jacket stops the 6 rounds, the front hard armor panel of this bulletproof jacket stop the 6 rounds of sniper round, which is as per the level 6 of BIS standard 17051. So the sniper round is basically 7.62 into 54 R API grade. So this is having a special hybrid composite made of the boron carbide and ultra molecular weight polyethylene. So these are the few structures and the combination of the material, because in the bulletproof jacket we are using the hard armor panel, then the hard armor panel is always backed with the soft armor panel. So these are the some sequence that are being used for making this thing. And again here these are the few more examples where the same type of the material are being used for making the blast suit and the helmet this thing. So if we just see that there are the few things which is important if we understand the mechanism of the stopping the bullet by any of the hybrid composite. So here we can see that the RSC core bullet is stacking to the ceramic phase, and the ceramic is being converted into the fragments, and the cracks are being generated. So the most of the impact energy of the bullet. So by the simulation we observed and we estimated that around 85% of the impact energy of the bullet is absorbed only by the ceramic, and the rest of the 15% has been absorbed by the backing composite on which the ceramic is bonded. So here the properties of the ceramic plays a very important role, and these are the we are also using the some type of the foams at the back side of the pattern, which will absorb the shock waves and the thrust. So these are the some properties of the foams that are being used, and this is a picture where this is a ceramic plate made of the boron carbide. So we just see that the what improvement we are doing in the ceramic. So we are adding some type of the ingredient side of the air beauty sector, where we are improving the fracture toughness. So here in the starting this plate, you can see that we can see the cracks because as per the BIS standard, before when we are going to do the project testing over the panel, this hard armor panel has to be dropped from a height of 122 centimeter 2 times on the RCC floor. This is the part of the mechanical durability test before the actual testing of the bullet. So we can see that there was some issues of formation of the cracks in the drop test, but when we have used some type of the foam and some improvement in the when we have added the ingredients into the ceramic, so the fracture toughness of the ceramic improved from 3 MPa root meter to approximately 4.5 MPa root meter. So we can see that we have stopped the formation of the cracks in the drop test, and this helps in the stopping of the bullet during the actual testing. So these are the key important properties of the ceramic material that we are using, like the hot-melt boron carbide, and the silicon carbide is also being used, but the density of the boron carbide is around 2.5 gram per cc. So this is the lighter in weight. So this is the reason why all over the world the boron carbide has attracted the researchers to do the research, so that when we are making the bulletproof jacket or something like that, the weight will be less. Even the some properties of the silicon carbide are superior to the property of the boron carbide, but still the boron carbide is having the advantage of the weight being the lower density. Just do the comparison, the density of boron carbide is 2.5 and while the silicon carbide is 3.1. So we used to gauge a lot of things for the weight part. So these are the some of the properties that being used, but the mainly focus is on the silicon carbide and the boron carbide. So some of the latest grades of the ultra molecular weight polyethylene that are being used. So these are here in the table, and here the this when we see the picture of the bulletproof jacket, the outer fabric of the bulletproof jacket also plays a very important role, because when this has to stop the API bullet, so which is called the armor pierce incendiary. So the bullet is having a special coating of the phosphorus which creates the incendiary effect. Means upon impact that will try to create the spark, and if that thing is not if the fabric is not the fire retardant fabric, so there will be always the probability of catching the fire by the bulletproof jacket. So the outer carrier, which is the housing of the hard armor panel, also plays important role, and these are the few of the important things that need to be addressed while we are using the material. And these are the some property of the foam. So basically, we just see the what are the important property for the armor gate ceramic to be used as a front facing. So the density should be less. It should have the high stiffness and the modulus. Hardness is extremely important, because as I told in the starting that now we are having the hard steel core bullets. So the front facing has to be hard. So hardness of the ceramic plays a very important role, and the ceramic should also have the high fracture strength. Fracture toughness is also very important, because if the fracture toughness is low, so the formation of the cracks upon the hit of the bullet will be more. So that panel will not able to withstand the multiple hits of the bullet. So we should have the high fracture toughness for the ceramic. The compressive strength is a very important role, because what we have observed the different grades of the ceramic. If the compressive strength is and in fact we have estimated the dynamic compressive strength by using the Spit-Hopkinson pressure bar. So if the dynamic compressive strength is lower than 2000 MPa, so that ceramic will not perform well. And when we are doing the simulation, so we are also estimating the one property which is called the HEL, which is the Higino elastic limit. So for the boron carbide, this elastic limit is 18 GPa. So when we are doing the finite element simulation, so this property plays a very important role to estimate whether the ceramic will be able to stop the bullet or not. So since here the testing part takes a lot of time and the expenditure also. So in our lab at Kanpur, we are also extensively involved in the finite element simulation studies for the different type of the combining for different grades of the ceramic using the apps, this thing. So we have also got a good core expertise in the lab for doing the simulation study. These are the some more detailing things, what the different properties which has been explained over here. So all the properties are there. So the fifth one is the boron carbide. This is the best for the making the bulletproof jacket type of thing. And these are the some of the processing details that what we are doing for making the boron carbide. So these we are starting with the powder, and then we are doing the sintering. So some of the like the three grades of the boron carbide. So the previous one is the hot press boron carbide, and this is the reaction bonded boron carbide. In the reaction bonded boron carbide, we are first making the slurry. Slurry is having the optimum combination of the 14 types of ingredients and that slurry is converted into the green body by the induction molding, and then that green body is again sintered in the temperature range of 1600 degrees centigrade to make the product. So here the estimation of the properties is also very important. So these are the few formulae where we can estimate, and one of the important property which is called the dynamic compressive strength. So we are estimating at a IIT Kanpur because Professor Venkat Nayan sir is there. So he is the core expert and he is also my guide also. So high strength rate property means the dynamic compressive strength using the split Hopkinson pressure bar, because the ceramic is not easy to handle, and the doing this test for the different grade of the ceramic requires a lot of expertise for the preparation of the specimen, and also to do the testing because a lot of sample goes waste also. So this is a special technique, and we are using the facility of a IIT Kanpur. So we are doing this test, and these are the in fact about the BIS we are doing the testing. So there is the conditioning protocol testing as per the BIS, where all the hard armor panels are exposed to a specified temperature, or temperature is 65 degrees centigrade at the 80% RH, and that holding time is for 10 days. And then after the 10 days, that hard armor panel are exposed to the cyclic temperature here, the minus up to lowest temperature of minus 15 and goes to the 90. And then the hard armor panel at the 90 degrees centigrade holding time of 2 hours, that is taken out, and this hard armor panel has been dropped. You can see in the picture, this is the drop test equipment. So here the this hard armor panel, after taking out the 90 degrees centigrade, the hard armor panel is dropped 2 times from a height of 122 centimeter, and then we are doing the X-ray, and then if that panel is found to have some type of the cracks, so the cracks will be identified in the X-ray, and the bullets will be intentionally fired over the cracks, because those cracks will be having the weakest point. So the testing protocol of the bulletproof jacket is very stringent, and this is the reason why the selection of the materials, especially the ceramic, is a very important role, because if the drop test, if we have found the cracks, so that cracks will be differently attracting the bullet, because the aiming of the bullet will be intentionally aimed at those cracks. So here the important thing is that while we are doing the processing of the ceramic, the fracture toughness should be high, so that at least in the drop test we should not have. These are the actual testing of the bulletproof jacket. There is one DRDO lab at Chandigarh, which is TBRL. So we are doing all the testing of the bulletproof jacket and helmet in the TBRL. So my thanks especially to the Director MSRD and to Dr. Venkat Nayan sir and the TBRL lab also, because our testing, and thanks to the same 2024 team. Thank you.
Thank you for a very interesting presentation, sir.
I would like to request Session Chair Dr. Kumar Sambhav to facilitate Dr. Parihar. Now I would like to request Dr. Pallav Gupta and Dr. Anup Kumar Shukla to facilitate Dr. Kumar Sambhav. It's over. Thank you. Thank you, sir. Sir ने बोल दिया।